and see that the whitening transform allows us to transform this difficult problem of identifying a signal in colored Gaussian noise to a simple problem of identifying a signal in white Gaussian noise. And we threshold that by a criterion that we are able to choose to determine whether or not we have a likely signal present. We can also transform this into the frequency domain by taking the Fourier transform of this equation, and we see essentially that we're taking the product of the frequency response of the signal of interest with the conjugate of the frequency response of the data divided by the power spectral density, which itself is defined as the Fourier transform of the covariance matrix. And we integrate that over the frequency domain, and then we normalize it by the Fourier transform of the denominator of the definition of L at the top. So we can work in the frequency domain if the noise is stationary, or we can work in the time domain, or we can work in a joint time frequency representation like with wavelets, which is how we do it. Okay, so now I'm going to tell you the story of TOI 715b. So this test object of interest was first in the catalog as test input catalog, or TIC 2719711330, and this was a signature of a habitable zone planet. About, let's see, it's about 1.5 Earth radii, so almost certainly rocky, and a 19-day orbit. And it's situated from its star, which is a cool M dwarf, about a quarter the mass and the size of the sun. It receives about 67% of the radiation that we do, putting it comfortably in the conservative habitable zone. And the paper by Dransfield et al. Also announced the discovery of a second candidate planet that we call TIC, and then we give it the phone number, then .02. They identified it as having an SNR of 13.8 sigma, a period of 25.6 days, and a radius of about 1 Earth radii. And this was very puzzling to us because they also announced that the SNR that they recovered for the first signal, which we also identified, was about 31 sigma. As you can see on this plot of this data validation summary report, I've circled here the SNR that we measured was about 18, or about half that they measured. And how can this be? The SNR of a signal is an intrinsic property of that waveform and the stochastic noise in which it's embedded. And so everybody who analyzes the same data looking for the same signal should get pretty much the same answer for the SNR, but they're getting about double what we are. So this became a detective story, and I had to ferret out the details of exactly what they were doing. And in fact, they are essentially applying a smoothing pre-filter to their time series after they detrend it, and then passing it through a simple matched filter. So in this model, detrending the time series with a cubic spline fit is assumed to generate a residual time series that's governed by white Gaussian noise, and you put it through a simple match filter. But in between the simple match filter and the detrending, they put this smoothing algorithm. Nevertheless, we did not detect the signature, but we were able to run our system in such a way so that we could see what we would have ascribed the SNR being, and we limited it to no greater than 5.5 sigma. That's not significant. Our threshold is about 7 sigma, so there are lots of spurious signals, largely instrumental, that can reach a level of 5.5, and so we would not consider this to be significant or worthy of being called a planet candidate. But our SNR was clearly not 13.8 sigma, which would be a strong signal. So to investigate this, once we learned what the smoothing pre-filter was, we inserted it into our transiting planet search. And when we ran it, we obtained nearly identical results as without it. And that's because TPS uses an adaptive noise compensating match filter. So it can sense and account for the correlation structure of the observation noise or that imposed by a smoothing pre-filter. Okay, so a couple of years later, we got a third year of data. So I've done a very poor job of explaining what's going on in this summary report. At the top, we have the full time series. The green lines indicate when the transits are excuse me, the blue triangles indicate when the transit is occurring. I think the green indicates when we had momentum dumps. We have a zoomed version of the folded signal down here at the third panel. But again, even though this is a dip, we limited the SNR, constrained it to no more than 5.5 sigma, and it didn't grow with the additional transits that are ostensibly accompanying the signal. It's about the same significance as it was with only 2 years of data. And so that means that this is unlikely to be a genuine transiting planet signature. Okay, so can we explain this from a theoretical perspective? Well, Dransfield et al. Used a Savitsky-Golay smoothing prefilter, and a Savitsky-Golay filter moves by sliding an odd-length k-point analysis window across a time series, and in each analysis window you fit an mth order polynomial and replace the central data point with the value of the fitted polynomial at the center of the window. So an SG-MK filter is essentially a moving average filter that smooths the input time series and reduces the apparent scatter of the observation noise. In fact, they use a third-order 11-point filter, and indeed, if you apply such a filter to a zero mean unit variance white Gaussian noise time series, it reduces the RMS variation by a factor of 0.45. And so here on the bottom left, I have a graph of what the filter coefficients look like for this 11-point filter. And then on the right, I have a false color image of the covariance structure imposed on the time series by this filter. And so the problem that's happening is that this filter is reducing the scatter on the data, but at the cost of imposing this correlation structure. If you don't take the correlation structure into account and just estimate the SNR by the RMS of the resulting time series, you're going to get the wrong answer because you're ignoring all of the off-diagonal terms. So in this graph, what I'm showing is on the bottom is a white Gaussian noise realization with a transit signal in it, and then on the top in the orange or red is the result of applying a Savitsky-Golay filter, third-order 11-point filter. So you can see, yes, indeed, it makes the transit more readily apparent, but it also correlates the data points, so they're no longer independent, right? So the problem is if you apply a smoothing filter, you're imposing a correlation structure, and what that means is that you're reducing the number of independent samples, and unless you take into account the reduction in the number of independent samples, when you estimate the noise power, you're going to get the wrong answer. So it's also problematic from other perspectives. So if we look at the zero plot, the pole zero plot for this filter on the left, we see that we've got eight zeros spaced around on the unit circle, and then we've got two zeros of this filter, one inside the unit circle on the real axis and one outside the unit circle, close to a value of 2 for the real component. And what this means is that these zeros on the unit circle mean that you destroy information at those frequencies, right? And the zero outside the unit circle means that this filter, it does not admit a stable causal inverse filter. And so that means that when you apply such a filter to a time series, information is irretrievably lost. You cannot reconstruct the original time series from the output time series. It's impossible to do. Nevertheless, the covariance matrix is non-singular, and so you can implement a whitening filter. And so on the right here, what I'm showing is in blue, which is almost hidden by the yellow, is the power spectral density of the original time series. The red is the power spectral density as a function of normalized frequency once you apply the Savitsky-Golay smoothing filter. And then the whitening filter recovers the yellow power spectral density. So it does a pretty good job of doing this. You can see there are discrepancies at the normalized frequencies corresponding to the zeros on the unit circle, but it does a pretty good job. And so what I did was to study this was generate 10,000 realizations of 2048-point white Gaussian noise time series, adding a 65-point long flat bottom transit of depth 2. This gives us a theoretical SNR of 16 sigma. It's a very strong signal. but very similar to the signal of the first planet that we found in the test data, and implemented simple match filter. And the distributions would be this green distribution on the graph, centered on 0. That would be the null statistics, so it has a Gaussian profile. And then when the transit is present, then you see the blue curve for the distribution. It's got a unit variance, and it's got a mean of 16.125. So it agrees with our theoretical predictions for how this should work, given our understanding of the noise and the signal. So in step 2, we applied a Savitsky-Golay third-order 11-point filter to both the data and the signal, and we repeated this experiment. And so instead of obtaining a null statistical distribution that's unit variance, instead it had a distribution of 2.17. You can see it here in the yellow. So it does have a mean of 0. Under the alternative hypothesis, when the transit was present, its scatter or RMS was 2.38, and the mean value was 32.75. So that's this purple out here. So that means that when they measured 31 sigma and normalized, that was because they weren't normalizing their distribution properly. They were normalizing it assuming that their null statistics had unit variance, but they don't. Their variance is about double that. In the third case, we implement the noise compensating match filter using the autocorrelation sequence of the Savitsky-Golay filter to take the time series from the second experiment and see if we can recover the original statistics. And indeed we do. So in fact, there's no difference between the distribution for the null statistics between case 1 and case 3. The whitening filter does its job, and we're able to recover the original statistical properties of the detection statistics. And again, when the transit is present, we're able to recover a distribution for the under the alternative hypothesis that has unit variance and a mean of 16.12. So very, very close to what we expect. So this is a cautionary tale for people who are data scientists that aren't familiar with the theory underlying transit detection or detection theory in general. Inserting smoothing filters in the signal processing chain will artificially boost detection SNR because it increases both the mean and the variance of the resulting detection statistics. And you can only know that when you're applying this empirically if you apply it to a large number of cases and actually pay attention to the scatter and the resulting null statistics, which clearly the authors of that paper did not. So I'd like to conclude by saying that stochastic signal processing methods have contributed significantly to the discovery of almost 6,000 planets to date. In fact, the wavelet-based match filter we use for Kepler and TASS has contributed to about 73% of the known transiting exoplanet discoveries. Stellar variability does present a fundamental limit on the detectability of transiting Earth-like planets, but adaptive match filters can provide near-optimal detection of Earth-sized transits and characterize the observation noise. As I said before, applying ad hoc pre-smoothing filters and not using a noise compensating approach that actually characterizes the stochastic noise process properties is very dangerous and produces artificially high SNR estimates. If you use such a filter, you cannot compare your SNR estimates to anybody else. And that means that we can't actually compare our results because 10 sigma means something, right? A 10 sigma detection means a very specific statistical thing. And we don't want to perturb that. We want to be able to communicate to each other about the strength of the signals we're finding. And we ought to be able to look at the same data and get the same result, or a result that is comparable, even if we're using other algorithms, regardless of whether they're Fourier domain techniques, time domain techniques like Gaussian processes, or joint time frequency representations like wavelets. So with that, I'd like to thank you for your time and attention, and I welcome any questions you might have.
Okay, thank you, sir. Any questions from the audience?
Yes, ma'am. There's a question from the audience.
Okay, very good.
What alternative data processing techniques can be used to prepare light curves for transit search?
Right. So, what we do is essentially we do a pre-processing step where we identify and remove instrumental systematics. That's a whole other topic, but essentially what we observed with missions like TESS and Kepler is that there are instrumental properties that change over time. Many of them are due to the fact that the spacecraft and instrument cameras or telescope are in orbit. And in fact, the changes in the thermal state of the camera or telescope can change the focus, for example. And that means that changes the point spread function or the quality of the images, and that can perturb the measurement of the brightness that you obtain. You can have all kinds of systematics. So generally speaking, we try to identify and remove those as best we can before we apply a match filter search. Ideally, you would actually combine those together and do a joint detection, and not just the noise characterization that we do, but you would also identify and remove instrumental systematics. That's much more computationally intensive, and given that we're looking for very weak signatures, weak transits that occur very rarely, we're pretty safe in assuming that identifying and removing instrumental systematics, because they're happening all the time. They're continuous waveforms where lots of action is happening. We can remove those with confidence that we're not significantly degrading our sensitivity to weak or signatures of transiting Earth-sized planets. But I've seen implementations that rely on frequency domain estimates of the PSD that can then convert it into correlation matrices or covariance matrices. So in these cases, those practitioners are assuming that the stochastic noise process is stationary over the duration of the observation. And so there are many different ways to peel this onion, so to speak. But those are some of the ways that people have done so. Are there any other questions? Okay, well, if not, I thank you for the opportunity to share some of my research with you, and I hope that this topic is inspiring to you. Yes.
Excuse me, I have a question.
Sure.
Yeah, what are the trade-offs between different data processing techniques such as smoothing, filtering, and detrending?
Okay. Well, in fact, you can view this Vitsky-Golay filter as a detrending algorithm, right? So when we ourselves talk about identifying and removing instrumental systematics, we talk about co-trending those terms out of the light curves. And the idea there is that we try to only remove signatures from the time series, the flux time series or light curves, that we can confidently assert are instrumental features. Whereas when you talk about detrending is usually the application of some kind of bandpass filter, either a low-pass filter or a high-pass filter with arbitrary cutoff frequencies in order to make the time series more easily understood visually. So it's really, from my perspective, really bad practice to apply detrending algorithms. Because when you think about it from the perspective of information theory and detection theory, you want to preserve as much information as possible until the very last moment when you actually make a decision that the signal is present or it's not present. And the application of a detrending algorithm removes information that should be presented to the noise compensating match filter. So I hope that helps, but one has to be very careful about what signatures they're removing from astronomical observations in order to ensure that you're properly interpreting the data.
Okay, thank you, sir.
Thank you, sir. We wanted to express our heartfelt thanks for your participation in SPIN 2025. Your talk was very informative. Thank you, sir. Now I invite Dr. Richa Sharma to present a certificate to Dr. John.
Thank you, sir, for sparing your valuable time. Thank you so much, sir.
Well, thank you. It was my pleasure to be here with you, and I look forward to the other talks.
Yes, sir. Thank you so much.
Thank you, sir. It is our great privilege to have Dr. Subodh Varia with us today.
Good morning, ma'am. Good morning.
Good morning, sir. Good morning.
Good morning, sir.
Good morning, ma'am.
Dr. Subodh is a professor of electronics and communication engineering at the Institute of Engineering and Technology, Lucknow, Uttar Pradesh. He received a doctorate degree from Motilal Nehru National Institute of Technology, Allahabad, India, a Master of Engineering degree from Jabalpur University, Calcutta, and BTech degree from HBTI, Kanpur. He has more than 29 years of experience in teaching and research. He has served as a scientist lead in defense research and development organization and graduate engineer at Hindustan Aeronautical Limited, Lucknow, from 1994 to 96. He has published more than 150 national and international papers in various journals and conferences. Dr. Subodh is actively associated with membership for professional societies as a lifetime member of the Institute of Engineers. It is a privilege to have you, sir. Welcome once again. So, would you like us to announce the paper presenters, or would you prefer by yourself?
Sound is not clear.
Sir, can you now hear me?
Ma'am, sound clear नहीं है.
Okay, sir. We are inviting our paper presenter
Oh.
113. Now it is audible to you, sir?
Yes. Okay, ma'am.
Okay.
Fine.
Paper ID 113. Are you there? Lajwanti Singh.
Hello. Good
Hello.
morning. Am
Good
I on?
morning. Yes, you are audible and visible too.
Yes, ma'am.
So can you say your ID proof if you have?
Yes, ma'am.
In front of camera you can share.
So this is my ID. I'm pursuing PhD from Vanasthali Vidyapeeth. I hope it is visible.
Yes, it is visible. You can proceed.
Yes.
Okay, hand over to you.
Fine. I'm sharing my screen right now. I hope it is visible.
Yes, it is visible. Go to your first slide and put it in slide only.
So starting with my presentation, I'm Lajwanti Singh, pursuing PhD from Vanasthali Vidyapeeth. Today I'm here to present my research work, which is based on designing and simulation of a photo detector using the platform SCAPS 1D simulator. Before starting with the presentations and the results obtained, I would share the outline of this presentation, that is starting with the photodiode layered structure and a perovskite material, And this design is being simulated on a software that is KEPS 1D simulated design. It is also used for LED designing and also used for photo detector designing. Then the presentation is carried with the results and discussions, and then with the conclusion part. So, starting with a photo detector, it is a basic semiconductor device which is used or actually identified for using a diode in a reverse bias situation. As we all know, diode is having a leakage current when it is work in reverse bias, and that current is not useful. But when these direct band gap materials are illuminated with the light, they actually contributed to a current which is named as illumination current and shows multiple applications. So depending on the wavelength of the light incident on this device, that is ultraviolet, VIS range, near infrared range, or other microwave ranges or other NM ranges, we have number of applications like photo medical imaging, pollution detection, thermal imaging, chemical analysis, and so on. So basically, what this photo detector do, it receives that incident light, it generates the hole and electron pairs, and these electron pairs follows the path of minority carriers and add on to the dark current. Now, why we are discussing this photo detector? We have number of papers and number of photo detectors available with the low cost. Actually, we are focusing on the replacing the inorganic materials with the organic ones, and especially in organic materials, I am trying to replace this perovskite, this lead content with the perovskite material, specialty lead free. So now clarifying all these things, I would like to show the structure. This is the perovskite photodetector structure, which consists of 4 layers. Moving from bottom to up, we have a TCO layer on which light actually falls. Then the ETL, electron transport layer. The main highlight or the main key layer of this photodetector is the absorption layer, which is used as perovskite material in my research work. Then the next is hole transport layer, and the last one is an electrode. So we have number of materials for choosing this HTL, perovskite, and ETL material. Till now, the work has been done with the lead-free perovskite material because perovskites provides number of key advantages. Let's go with this perovskite structure. So this is the cubical crystal structure of a perovskite material. It is based on a chemical formula AMX3, where A and M represents different materials. The halide ions, the anode and cathode materials. Number of options are available for this formula, and I am working on the key feature, that is M. This lead is replaced by the antimony, that is SN, to make a green photo detector which is suitable for this society, to make the society lead free, as when it is infused in the air or in the water or land, it is harmful for us, for other living beings too. And choosing the halide ion, I chosen the bromide, right? So this material is being tested on this software, this lead free content, for making a suitable photodetectors. We have number of key benefits for the perovskite materials, that these provides high tunable band gap, which is the prime requirement of the semiconductor devices. It shows low cost, it shows high carrier mobility. The higher the mobility, the more will be the current. It shows large carrier diffusion length. It shows high absorption coefficient. So these are the key advantages of using the perovskite, and replacing a lead content with a lead free content is for making a healthy environment or a toxic free environment. So moving on to my work, I have chosen number of materials for all these layers, finally concluded with this 5-layer device structure. Moving from bottom to up approach, initially I have a TCO layer that is named as glass substrate on which light actually incidents. The next one is fluorine doped tin oxide, that is a transparent oxide layer, which is actually a combination of this TCO part. The next one is an organic PCBM layer. It works as an electron transport layer, right? And it is related to the methyl contents to show that organic part. The main key feature is this, the cesium antimony bromide layer, which I was talking as a lead-free bromide, lead-free perovskite material. And the last one is the MOO3, that is molybdenum trioxide, which works as a hole transport layer. So combining all these three layers, a finally 5-layer photodiode structure has been designed, which is visible on the device. The last one, that electrode layer, I have chosen the silver AU for the conducting medium. Right now, when this device structure is simulated on the SCAPS 1D, so talking for the software, that is SCAPS 1D, it is I think it is designed 10 or 15 years back by the Marx Bergman, and I'm very thankful to him for providing us such a wonderful platform where it is actually practically possible to analyze the different features, electrical features of a photodetector. There we can see how the current varies with the voltage, how the capacitance varies with the voltage, what is the responsivity, what is the quantum efficiency of the photodetector, which earlier was bit difficult with the other platforms available. Moving on to the result and the discussion part, when we simulated this structure, starting with the first result, that is the energy band diagram of the device. This is the graph generated from the software itself. It shows the energy levels with the distance in the micrometer range for the device. It started it showing the energy band diagram for all the 5 layers which are added or which are being used in this photodetector. Later on with the simulation, I got the graph, that is first one is for JV curve, that is current versus voltage, and basically that current is represented in the current density part. I've simulated this device at the different temperatures. Like we are wearing 2 parameters. The first one is the light. The bandwidth for the light incident is 300 to 900 nms, and the same device is simulated at the 3 different temperatures. The first one at 300 degree Kelvin, later on with 375, and the last one showing with the 450 degree Kelvin. So we are showing the device current density parameter with versus voltage on 2 different parameters. The first one with the incident range and the second one with the temperature. Shows as we are increasing the temperature, the point where the graph shoots up, like initially it is showing very less value as a reverse bias diode shows, but when light incidents and the carriers are well absorbed by the device, around at 1.2 the curve shoots up. So with the increasing temperature, this shooting up of the curve or actually getting the illuminated current is the response time is showing less. It shows earlier as compared to the increasing temperatures. The first parameter was this. Now the second parameter which is evaluated is the quantum efficiency with the wavelength. The same, the device is illuminated from 300 to 900 nm, and we can see after 600, more specifically 610 nm, the quantum efficiency drops down. That means the device was not able to generate that visible current or that visible response. So the effective wavelength range where this photodetector works is 300 to 600 nm. The same device is evaluated for this quantum efficiency at different temperatures, and the graphs are showing the black one line is showing for 300 degree Kelvin, and as we increases the temperature, the quantum efficiency drops down. The saturation or that linear region for 450 Kelvin is quite less as compared to the device working at the room temperature, that is 300 Kelvin. The maximum quantum efficiency we may show, it is near about 75.8%. That is the maximum or the peak point of that quantum efficiency. So this is the second parameter evaluated for the photodetector. The third very important parameter for the photodetector is responsivity versus wavelength curve. The responsivity is the main key feature on which we categorize a photodetector. It shows how the device is responding for the incident light or how much current is being generated. It is absorbing that light and producing the equivalent illumination current. So again, the device is specifically illuminated with 300 to 650 nm, as after this quantum efficiency drops down and same the responsivity drops down. So the responsivity versus wavelength curve is shown here again with the different temperatures, and it is high for 300 Kelvin, and as the device is heated up, as the device is being illuminated at the high temperature, that responsivity decreases. So maximum range for the responsivity is shown here. This is the main parameter which we have evaluated on for the photodetectors. So this was the whole work which I have carried right now. Moving on for the further work, I am working for the detectivity range, and the main parameter on which I am working is trying to reduce that dark current when the device is not illuminated and the maximum current. So I think that would be the next key feature to be evaluated for the photodetectors for this work. Moving on to the conclusion part. Initially, as is discussed, the device structure. We have made a lead-free perovskite-based photodetectors, which is simulated on the detectors, that is CAP1D simulator. Then the device was illuminated and checked or verified for the different temperatures. For this, initially, various material parameters are chosen, that what should be the energy gap, what should be the mobility, what is conductivity, NA and ND parameters, what should be the, the interfacing between the two layers, what should be the defects so that the device would work more practical. These parameters are chosen, and then the device is illuminated for the given range and tested for different temperatures. The observed parameters as shown are JV, quantum efficiency and responsivity, and plotted against the different temperatures. The references I have included in this work and the presentations are given here. Thank you. And I would like to invite if any of the query or discussion. Sir, yes, sir.
Madam Singh
Yes,
is
sir.
a very good topic, because you are choosing a lead-free material.
Yes, sir. Yes,
Okay.
sir.
In your presentation, there is some comparison between the previous work result as compared to
Yes,
your
sir.
result.
Yes, sir. Yes, sir. There is a comparison which I have not included in the presentation, but is included in the paper. I have compared the device with lead content and another lead-free material, that is CS3 material, and then my antimony bromide material. I may
Okay.
show that the table also.
Ma'am, in your structure, you use 5 layer in this structure.
Yes, sir.
In the conventional photo diode, how many layers are used?
Sir, in the conventional, 3 main layers are there: ETL, HTL, and the absorber layer. And
Okay.
beside this, we need a glass substrate on which we can incident the light. We have added a TCO layer for providing that conducting medium and making the device more practical. Because in general, when we device is fabricated, more of the noise, more of the losses are there. So to
Okay,
make
ma'am.
that practical approach, we have
Yes.
added 5 layers.
Yes. Ma'am, what is the maximum range in terms of wavelength in your work?
So the maximum range is 620 nm, because after that my device drops down to the around 10% of quantum efficiency. So it is working for the visible range that is 300 to specifically 600 nm range.
Okay, ma'am, this software is a licensed software or some crack version is
No, sir. This is
available?
no, sir. This is a licensed software. We have to mail to the Marx Burglum personally, dealing with around 15,000 users right now in the worldwide. I have communicated with them and got the license to work on this. For this, we have to register on their platform. After then, we are able to use this software.
Okay, ma'am. Thank you.
Okay, sir. Thank you, sir. Any other query?
No more questions. Thank you so
Okay.
much.
Thank you.
Okay. Next paper ID is 127. Paper ID 1. Yes. Okay.
Hello, ma'am.
Yes. Can you share your ID proof? Okay. Fine. You have 10 minutes for the presentation, right? Go ahead.
Ma'am, can you close the slide?
Ms. Lajwanti, can you unshare your screen? Ravinder, you can share your screen.
I can't share the screen. Okay.
Okay, now you can. Yes, it is visible to us. Put it in slideshow mode. Okay, fine.
Hello, ma'am. Hello, everyone. Good morning. I am going to present the research work on the design and implementation of high efficiency 3.3 to 1.8 buck converter in 180 nanometer CMOS. Introduction. Like a buck converter is a DC-DC step-down power converter that reduces input voltage to the lower output regulated voltage, and it is used in power management for various electronic applications. Like why buck converters are essential? High efficiency, battery powered and low power systems used in microprocessors and embedded systems and power electronics. Like applications of the buck converters, voltage regulator is a microcontroller in microcontrollers and ICs, power supplies for mobile devices, IoTs and industrial applications. Energy efficient systems such as solar power and electric vehicles. Like our research aim to design a high efficiency buck converter using 180 nanometer CMOS technology, achieving a stability voltage regulation of 3.3 volt to 1.8 volt with 0.5 ampere output current and with efficiency of more than 81%. And these are the objectives. And efficient voltage regulation. The primary objective is to design a buck converter that effectively step downs the voltage from 3.3 volts to a stable 1.8 volts, ensuring the reliable power delivery with output current of 0.5 ampere. And high power conversion efficiency. The design aims to achieve efficiency greater than 81%, reducing the power losses and improving the utilization. Compact and integration solution utilizing 180 nanometer CMOS technology ensures a compact integrated design suitable for portable and low power applications. Stability under varying conditions. The converter should maintain a consistent performance across different load temperatures and input voltage variation. Implementation of robust feedback mechanism using voltage mode control to dynamically adjust duty cycles and ensure stability output voltage under the transient conditions. Low output ripple and fast transient response. optimize the passive active components to minimize voltage ripple and ensure the converter reacts swiftly to the load changes. The literature survey which are which we have used, like we have used, they are mainly of two types, like synchronous and non-synchronous, and in that voltage mode control, current mode control, and other which are uh, done through the pulse width modulation, and alternatively the pulse frequency modulation is the type and proposed method. Like we have used the voltage mode control, uh, the feedback mechanism. Like importance of the voltage mode control, it is it provides a precise output voltage regulator where voltage mode control excels to maintain a stable and accurate output voltage. It utilizes a feedback loop that continuously monitors the output voltage and adjusts the duty cycle of the switching element, typically a MOSFET, to ensure it aligns with the desired reference voltage. This meticulous control is vital for powering sensitive electronic components that require a consistent voltage supply. Fast transient response. Voltage mode control exhibits a swift response to sudden change in a load current. The feedback loop rapidly detects deviation in the output voltage and adjusts the duty cycle accordingly. This again ensures the converter quickly recovers from transient event, minimizing the output voltage fluctuation. Simplicity in implementation. Voltage mode control offers a relatively straightforward implementation compared to other control schemes like current mode control. The control circuit primarily focus on monitoring and regulating the output voltage, leading to a more manageable design process. The working principle of voltage mode control. Here, the Vout is uh, Vout is divided by Vout voltage is divided by the resistor voltage and given input to the error amplifier. The error amplifier, the operation amplifier, compares the feedback voltage with the reference voltage, representing the desired output voltage. This error amplifier amplifies the difference between uh, the feedback voltage and the reference voltage. And this output is given to the comparator, input of the comparator. This comparator compares the voltage uh, between the error amplifier output and the saw voltage and provide a pulse width modulated output, and this and given to the input of the driver circuit. And this driver circuit amplifies the voltage and give to the feedback to the power switches. Circuit implementation. Let's come to the duty cycle. For duty cycle for V out of 3. V out of 1.8 and V in of 3.3 volts into 0.54 volts. This indicates the switch is appropriate of 54.54% of the time and off for 45.46% of the time. The average voltage output voltage is controlled based on the duty cycle. And the uses of the power switches, inductors, and capacitors. Power switch, when the power switch is on, connects the input voltage to the inductor, store energy in the inductor's magnetic field. When power switch is off, disconnects the inductor from the input, causing the inductor to release the stored energy, maintaining current flow to the load. Inductor stores energy during the on phase and release it during the off phase, ensuring continuous current flow and a controlling current flow. Capacitor uh, smooth the output voltage by storing and releasing the energy, reducing the high frequency repair. Energy conversion. Um, the switch inductor and capacitor works together to convert the input voltage to a stable, lower output voltage. Stability and ripple reduction. The inductor and capacitor work to minimize ripple and stabilize the output voltage. This error amplifier op-amp design. We have designed a 7-pack op-amp with current reference as 40 microampere gain of this op amp is around 65 dB, and gain bandwidth is around 30 megahertz. And the common mode voltage for the 1.8 to 1.6 volt. And this and we have introduced um, error amplifier, a type 2 compensator, used to enhance the stability and performance of the feedback system in the buck converter by introducing a pole zero arrangement. It provides 1, 0 and 2 poles in a type 2 compensator. Error amplifier. The error amplifier amplifies the difference between the actual output voltage from the voltage divider and the reference voltage, representing the distance. Compensation network. The type 2 compensator processes the amplified error signal through a network of resistor and capacitor, creating a transfer function with 1, 0 and 2 poles. Phase boost. The capacitor provides phase boost near the crossover frequency, increasing phase margin and improving system stability, reducing the oscillation. Stability and accuracy. The combination of feedback and compensation ensures stability, accurate output voltage under varying load conditions. Comparator. And comparator, a second op-amp acts as a comparator to generate the control signal. Here, there are two inputs. The one input is given from the output of error amplifier, and second input is ramp signal. Suppose if the ramp signal voltage is lower than the output of the error amplifier, then we get output as high voltage. And if error amplifier output is smaller than the ramp signal, then we get output as low voltage.
Sorry to interrupt you, Ravindra. Can you wind up your work?
Sorry, ma'am?
Can you wind up your work?
Yes, ma'am. That's concept. Driver circuit. Driver circuit, it is one of an important circuit in the buck converter. It connects the comparator to provide a smoother PWM waveform for dividing power transmission. Voltage amplification, like it provides voltage amplification and current amplification, and it also acts as a level shifter. It shifts the PWM waveform and isolation dead time insertion under voltage lockout. And here we have done band gap reference to provide the error amplifier as a reference voltage, where the output voltage is 0.9 voltage. Here we generates a stable reference voltage by combining two voltage source and complementary temperature behavior. Here it takes to provide a constant voltage with where even if the temperature varies. Here is the slope of the PTAT and CTAT voltage, and we have got the constant Vref voltage or SNO. And here is the ramp signal which we are providing to the comparator with the frequency of 20 megahertz, and the voltage is from 0 to 1.54 volts. And here is the simulation output voltage and the output current. We have obtained 1.8 volts as output voltage and current of 0.5 amperes. Here we have the output voltage of all the blocks, where we get output voltage of total buck converter, current, error amplifier, and comparator output and driver circuit output. And here the performance analysis, like our proposed work and specification of second paper which I have referred, and seventh paper. Feedback control method discuss various control methods for DC-DC buck converter with a focus of voltage mode control. Buck converter structure analyzes key components and their role in efficient power conversion. Efficient advantage. Demonstrated that switching mode converter is less power than a linear regulator. Implemented, designed a PWM buck converter using in UMC 1 nanometer CMOS technology with 20 megahertz switching frequency. These are the references which we have referred. Thank you.
Good morning, sir. You designed bug converter.
Yes.
Hello, I am audible.
Hello, sir. Yes, sir. You are audible.
You in your design, there is a two type of design. Some passive component is used such as switch, resistor, inductor, capacitor, and second part is a error amplifier, converter, and other band reference circuit is designed with CMOS design.
Yes, sir. CMOS technology we have used.
Okay, I agree. Which software is used to test your circuit?
Sir, we have used Cadence Virtuoso.
Cadence Virtual software is used for total testing design, or you use some individual test for error amplifier, converter test, band reference circuit, or
Like
so
we have used for error and amplifier, we have used MATLAB, sir, for the poles and zero locations. Sir. Rest all we have done in the this Cadence Virtuoso.
you have a you design a layout also.
Yes, sir. We have designed layout for.
So how the inductor and capacitor and resistor is designed by using as a component, as a passive component, or you can design with the help of CMOS circuit.
Like inductor is act as an off chip, sir. So in the layout part, inductor doesn't come, and capacitor and the resistors we have used centroid matching and interdisplacement matching for the resistors.
Okay. My last question is, in a comparison table, you compare your work with some reference circuit, but when the technology is different, because your work is 180 nanometer and some references says 130 nanometer and 65 nanometer. So how the comparison is take place when the technology is different, input voltage VDD is different, though the comparison parameter is not same, or you can not justify according to your work, because you design your circuit 130 nanometer or 65 nanometer. My question is, you some change in conventional or some design is reported in the literature, or you same use the reported design,
No,
only
sir.
the technology is changed?
No, sir. The literature survey, they have different circuits, and we have different circuits, sir. And they provide, they have done in the smaller technologies which provide better efficiency, sir.
No, my question is, you can you design your own circuit. So why
Yes,
you not simulate for 130 nanometer or 65 nanometer, then compare to the reported?
like for our future work is to do that only, sir. We are now comparing for 130 and 65 nanometer. We are designing
Okay,
for the lower nanometer.
okay. In your circuit design, some HSS and LSS component is used. You can define what is HSS and LSS?
In which part, sir?
Circuit design. Circuit. You show your circuit, na? Some
Yes.
MOSFET or some past transistor maybe shows like as HSS, LSS.
Sir,
Yes.
yes, yes. Sir, HSS means it is a PMOS circuit and LSS means the NMOS circuit, sir. It is an inverter like which the PMOS is connected to the VDD and VS then NMOS is connected to the ground, sir, and that is VSS. And here the driver circuit output is given as the input for these inverters.
Okay, fine. Thank you.
Thank you, sir.
Okay, thank you. Next paper ID is 161.
Audible, ma'am?
Yes, you are audible. Turn on your camera.
Yes.
Okay, share your ID proof.
Good morning, ma'am. This is Mohammad Ali, and I'm from KLA Tech University, Hubli. So this is my ID.
Okay. You have 10 minutes maximum
Yeah,
for the
share my
presentation.
screen.
You can share your screen. Yeah.
Yeah, is this visible?
Yes, it is visible.
Yeah. Good morning, everyone. I am pleased to present my research on design of low dropout voltage regulator with high gain and fast transient response. The paper ID is 161, and the presenter is Mohammad Ali, and my co-authors are Siddhant, Sujata Kodbagi, Sahana Kalur, and Trishti Joshi. Yes, this slide provides an overview of the key topics covered in this presentation, which includes the objective, literature survey, block diagram design, and conclusion. Yes, coming to the introduction to LDO. So first we need to understand what is LDO. So LDO stands for low dropout voltage regulator. So basically it is a type of DC linear voltage regulator which ensures that stable and efficient output voltage is stabilized even when the supply is very close to the output voltage. So in the analog and mixed signal system design, so these regulators play a crucial role by providing a clean and reliable power. With the advancement of VLSI technologies, where feature sizes and supply voltages are decreasing, the demand of high performance LDO regulators has significantly increased. So these regulators, especially these are used in battery power devices and microcontrollers, RF and communication circuits, and uh, and where the low heat dissipation and power efficiency are critical. So these LDOs are used. So the basic design of LDO consists of error amplifier and a feedback network, and which together ensure stable voltage regulation and adaptability in various application. So here you can see that the power supply, which is a battery, it is the input is not stable, but we need the output as 3 volt, stable 3 volt, so which is required by our many battery power devices like mobiles, laptops, and all. So next coming to the objectives. So the primary objective of this research was to design an LDO regulator which provides a stable output voltage of 0.8 volt and from an input of 1.8 volt, and the load is 20 milliampere, and also to ensure minimal voltage drop. Additionally, we aim to optimize loop gain and stability by maintaining a gain of at least 60 dB with a phase margin of 60 degrees, and also to prevent oscillations and ensure a proper transient response. Another key goal was to achieve a fast transient response with minimal undershoot, overshoot, and all. Next. This is the literature survey of the papers we have gone through. This table summarizes different LDO regulator designs, their key findings, method used, and best suitability. The first study improves load current range and transient response using charge pump LDOs and exponential ratio, making it ideal for applications needing fast response. Another study, it ensures presents LDO compensation techniques, helping in adaptive designs that need flexible compensation. Okay. Next, coming to the block diagram of an LDO regulator, here you can see that this is the error amplifier, which is a green color, and this is the MP is the PMOS pass transistor, and this is the R1, RF1, and RF2 are the feedback network, and this is the output capacitance, and this is the load current. So so the reference voltage is provided by the BGR circuit. It generates a stable reference voltage, and it is unaffected by temperature and supply variations. So this reference is compared with this feedback with the feedback from the output by the error amplifier, which then amplifies if there is any difference and adjust the PMOS pass transistor accordingly. So this PMOS pass transistor, it controls the current flow from the input to the output, ensuring a low dropout voltage. A feedback network continuously monitors the output voltage, and it provides necessary adjustment through a feedback loop. Additionally, the output capacitor, it helps improves the stability by filtering voltage fluctuations and enhancing transient response. So this design ensures low dropout operation, efficient power management, and stable voltage regulation. So if you take, like for example, if you take the current I load is changing from 10 milli to 100 milliamperes. So how this is regulated, we can take is that suppose if initially the current is 10 milliampere and it starts to increase into 100 milliamperes, then what happens is the uh, uh, the voltage at the Vout it's gonna start increasing, and the error amplifier, it generates an error signal. So the output of the error amplifier, it is connected to the gate of the PMOS pass transistor. So the VST of the PMOS pass transistor changes. So the ID also changes, which stabilizes again the Vout output voltage. So next. So this is this is the design. So uh, this is the error amplifier which we use as a PMOS folded cascode, and the reference voltage is given by the BGR circuit. It provides a stable and precise reference voltage, ensuring accurate regulation. So the BGR is designed to be temperature independent, and which helps maintain a steady voltage across different operating conditions. So the error amplifier, it plays a crucial role in voltage regulation. It compares the reference voltage with the feedback voltage and generates an error signal. So this is the error amplifier, which in this case we have used as a PMOS folded cascode op-amp, which provides high gain. Okay, ensuring it also ensures accuracy. So this amplifier reduces sensitivity to various in temperature and supply voltage. So the pass element, this is the M13. It is the PMOS pass element in our LDO. So it functions as a variable resistor controlled by the error amplifier. It adjusts resistance to maintain a stable output voltage. Compared to NMOS, PMOS transistor offer low power loss and heat dissipation, making them highly efficient. Okay, and this is the 10 kilo and 10 kilo. This is the feedback network consisting of a resistor divider. So this network, it takes a portion of the output voltage and it feeds it back to the error amplifier for comparison. So the error amplifier then generates the necessary correction signal to adjust the pass element accordingly. So the choice of resistor values determines the output voltage level. Here we have taken it as 10 kilo and 10 kilo. So this output capacitor is another component that improves voltage stability and transient response during sudden changes in load. This capacitor supplies additional current. It supplies additional current, preventing voltage spikes. So the type and value of the capacitor are selected based on the performance and load requirements. And finally, we have the 20 milliampere load, which is the specification of this. So, it also used to powered devices such as microcontroller sensors. So this load current is used. And coming to the, yeah, this is the transistor sizes. This table presents the aspect ratios of the key transistor used in our design. Proper sizing of transistor ensures a balance between stability or efficiency. Okay. Next, coming to the result section. So the design of LDO achieves a high gain of 74 dB, ensuring precise output voltage regulation. A high gain enhances the regulator's ability to maintain stability even under varying load and input conditions. So additionally, the regulator exhibits a phase margin of around 78 degrees, which guarantees stable output regulation without oscillations. And the unity gain bandwidth, which is unity gain bandwidth means bandwidth at when the gain is unity, it is 9.47 megahertz. Here you can see that 9.47 megahertz provides a balance between speed and stability. And next, coming to this is the PSRR of the LDO. What is first we need to understand what is PSRR. So it measures how effectively this LDO regulator suppresses the fluctuations in the input voltage. So our LDO achieves a PSRR of 40 dB at 10 hertz and 37 dB at 100 kilohertz, as it is shown here. So this means that input noise and ripple are significantly attenuated, and it also ensures a clean and stable output voltage. So we actually in circuits we need a high PSRR across different frequencies, as it minimizes the impact of power supply variations on the output voltage. Next, coming to the linear line regulation and load regulation. So line regulation quantifies the LDO's ability to maintain a stable output voltage despite changes in input voltage. So our LDO achieves line regulation of 12 millivolt per volt, which means that output voltage changes by only 12 millivolt for every 1 volt change in input, as it is illustrated. This tight regulation ensures that even the input voltage fluctuations, the output remains stable. And coming to the load regulation, it tells it tells how well the LDO maintains output voltage as the load current varies. Our LDO achieves load regulation of 0.15 millivolt per milliampere, which means that output voltage changes by only 0.15 millivolt for every milliampere change in load current, as it is shown here. And coming to the line transient and load transient response. So line response describes the ability of the LDO to handle sudden changes in input voltage. When an abrupt change in occurs, the LDO experiences 0.3 millivolt undershoot and 0.24 millivolt overshoot. So undershoot and overshoot here you can see in this figure. It's 0.34 and 0.5 millivolt with a settling time of 12 microsecond. A low undershoot and overshoot along with a short settling time, it compensates for input variations. And also the low transient response, it reflects the LDO's ability to handle the sudden changes in load current when the load shifts abruptly. So next, coming to the PVT analysis. So first we need to understand what is PVT. So PVT, it is a way to check if an electronic circuit works well in all possible conditions. Process refers to small P means process, which refers to small difference in how chips are made, which can affect performance. V means voltage. Voltage means the power supply may not always be exact and it can change slightly. And how the T means temperature, affects how fast or slow a circuit operates. So we test it. In LDO regulator design. PVT makes sure the circuit gives stable output no matter the manufacturing differences, power supply, or what is it, temperature variations. This help ensures that the circuit works reliably in real world application. So in our design, the PVT was conducted for the gain and phase analysis at temperature of 125 degree Celsius with and we got the worst gain case is observed to be 57 dB with the phase of 84 degree. At temperature of minus 40 degree under the same condition, the best case gain is 79 dB with the phase of 86 degree. And the coming to the result table. So this I all summarize this the result what we have got here. All the parameters like line regulation, load regulation, gain, phase margin, and PSRR at different frequencies, and also line transient response, undershoot, overshoot, and settling time, and similarly the load transient response. And coming to the concluding my part, we successfully designed and optimized an LDO voltage regulator that provides stable 0.8 volt with from 1.8 volt input supporting 20 milliampere By using a PMOS pass transistor and folded cascode error amplifier, we achieved high gain, minimal dropout voltage, and a strong transient response. Like future work could include the layout of this design and also implementing adapt compensation techniques and exploring designs in smaller technology nodes. So like 90 nanometer and 65 nanometer. Okay, these are the references we have gone through. Yeah, that concludes my presentation. Thank you for your time and attention.
Okay, you design a LDO, okay, and with the voltage range of 0.8 volt to 1.8 volt.
Yes.
And some simulation result also shows for line regulation, voltage regulation, transient regulation. My question is, what is the bandwidth? What is the frequency range?
It's 2 kilohertz.
2
3
kilohertz.
3 dB frequency is 2 kilohertz.
So this frequency range may be bandwidth may be increased by any change in the circuit, or this is the maximum 2 kilohertz.
So it's a 3 dB frequency is 2 kilohertz and the UGB is 9.47 megahertz.
9.47
megahertz.
Oh my. And you, Ajay, what is the power?
Sorry, sir.
Power. Power in your LDO, there is some power dissipation, variation, or some consideration. How much power is a low power device? What is the maximum power?
The power we have, it is not not included in the paper.
Achha, your design, which application is suitable?
Sorry, sir.
You design this LDO, which application is used this design?
So it can be used where the stable output voltage regulation is required, like in these are mainly used in microcontrollers and battery power devices and all.
Okay, thank you.
Thank you.
Okay, thank you. You can unshare your screen.
Yes.
Next paper ID is 238.
Yes, ma'am.
Okay, share your ID proof. Okay, fine. You have 10 minutes, maximum 10 minutes. You can share your PPT.
Ma'am, it is visible?
Yes, it is visible to us. Put it in slideshow mode.
Good morning, everyone. I am Pushpita Tiwari from IIIT Allahabad, Research Scholar in EC Department. And I'm very pleased to present my topic, my research work on design and simulation of biocompatible low frequency vibrational energy harvester with optimized Feller cantilever array. These are presentation flow, introduction, literature survey, methodology, simulation setup, result and discussion, conclusion, and references. Now, introduction. Pacemaker actually energy harvesting device needs my energy harvesting device convert ambient vibration into electricity, and in my work we use a human body motion, especially heart motion, heart vibration into the electricity, and that electricity is used by the pacemaker. So we want to remove the battery whichever used in pacemaker, which is very bulky and also very toxic, and it frequently needs a surgical replacement too. So we want to replace this battery with the help of energy harvesting device. We use a material like a silicone and PVDF, which is a very much biocompatible in nature, and biocompatible in nature means it is a very safe for our body so that we can use it. And this application is also used in leadless pacemakers, sensors, wearable devices. Previous studies also used the energy harvesting, but they use the silicon, copper,
PZT that used a lead content. So we want to replace this lead content in a biocompatible material, so that we try to move a silicon and a PVD of material. We can see this table. Silicon, the Young's modulus of a silicon is very low, that is 2.4 megapascal. That is a very flexible device. So that when we use a silicon as a substrate and a PVD on the layer on the silicon, so that it transfer strain from the PVDF, and it is much compatible device, so that we get a sufficient power for the our pacemaker. PVDF a piezoelectric material which works on the principle of piezoelectricity, that converts the human vibrations, especially heart motion, into the electricity, and we simulate these work. And this is a design. This is a only single cantilever design. We can see that a base design, base material is used is a silicon substrate over which PVDF is deposited, and a proof mass is also attached over there, so that when the human vibrate, then the this substrate move and create a electricity, which is used by the pacemaker. Now, literature survey, there is a very much work already has been done in energy harvesting device, but we cannot get a biocompatible material as in the range of a 20 to 30 hertz. That is a secondary vibration of hertz frequency, and we also see that there is a various shape like L shape, V shape, trapezoidal shape, spiral shape. But we use in this research work rectangular cantilever, which is a very efficient, and also its fabrication is very easy. So that mainly we focuses on the rectangular cantilever, and also there is a use of PZT, legonite, and copper substrate, SOI wafers. These all are not as much biocompatible, so it harm the human body. So that we use PVDF and silicone substrate. Both are very much biocompatible. Now we can see that limited studies on low frequency 20 to 30 hertz biocompatible energy harvester can be done. Methodology. Our work is performed on the COMSOL 5.5 simulator multi-physics model, and firstly, for model our device, firstly we define our geometry on the COMSOL 5.5. For geometry, we use unimorph cantilever. Unimorph cantilever, that means a unimorph device. Piezoelectric layer is only deposited one side of PVDF silicon substrate, and the device cantilever size is 4 into 19 into 0.50 mm. So firstly define the geometry, and after that we assign the material. We use two material, PVDF as a base substrate and silicon substrate, and over which PVDF piezoelectric layer are deposited. Frequency range, we put the 20 to 30 hertz because this is a high vibration frequency. We need to power voltage and current only this range of frequency, and when the energy harvester matches this range, gives the maximum efficiency and output. After material assignment, we give the physics and boundary conditions. We applied solid mechanics physics, electromechanical physics, and electrical circuit physics. Solid mechanics and electromechanical physics are used for the conversion of vibration into electricity, so that the coupling is required. So these physics are used for there. And fixed constant, we fix one end of the cantilever and second end is freely moved, so that the electricity can be generated. Methodology, this is a simulation setup of my work. We designed two type of design. One separate masses, and second one is mono masses. Actually, we design a parallel cantilever array in which we take 5 different cantilevers, and we use two parallel combination of 5 cantilevers array. In first design, we use a separate masses for each cantilever, and in second, we use a mono mass for all the cantilever. And we want to see what the comparative study over here, what the different parameters, what the different voltage, current, and power we can get from both of these two. So we can see different pros and cons of both of designs. From here, we firstly physical dimensions analysis. We can see their substrate silicon. The length width height of the silicon substrate is same in both the designs. Piezoelectric layer PVDF, length width are same, but height of each cantilevers are different. Actually, when we want sufficient power for pacemaker in the range of 20 to 30 hertz, so that the tweaking required. So we put the values of cantilevers, all the cantilevers piezoelectric thickness and the proof mass thickness are variable. If we put these values, trial and error method, we put the different values, and when we get a sufficient amount of energy and sufficient amount of voltage and current, then we get the result exactly whatever pacemaker required. Actually, pacemaker required about 10 microwatt to run, and in that's why I want that result. These are the result of my work. These are the result matrices. First table or table 3, this result says that my whole mechanical outcomes design. There are comparative tables, some separate masses and mono masses, because we designed two separate designs. First, separate masses and mono masses. After the result, we can see Maxwell capacitance, displacement, von Mises stress, and also the whatever the FC is means impedance is produced by the piezoelectric layer. At the end, we put same load resistance across the device so that maximum power transfer can take place, so that the load impedance of the device can also be calculated over here. Now, table 4, we can see that electrical outcomes for separate masses and mono masses are also there. There are a frequency range from 27 to 28, 29. So that these frequency ranges, we can see the voltage, current, and power variation with the help of this frequency range variation. We see the separate masses and mono masses both comparative table. We see that when there is a resonant frequency at which we get a maximum voltage, current, as well as power for monomass and separate masses both. But there is a power 43.2 microwatt in separate masses, while in monomasses we get 20% higher power. These are the result graph of my simulation result. We can see that figure 3a, and these are the comparative graph between monomass and separate masses. We can see the blue one is the separate masses. There are 5 cantilevers, so that 5 peaks over there, and when one cantilever has its resonance, so it works, it displays, and other, so that is why we get a broader bandwidth. And if we want a broader bandwidth, then we use a separate mass configuration. But if we need only more power, then we use a monomass, because monomass has a 20% more power than separate masses configuration. And besides there, the cumulative graphs are also there, so that there are 5 peaks over there, so that if we take a cumulative graph, then we see a small widening in the bandwidth also take place. So these are the voltage, current, and power respectively graphs, and also cumulative graphs of the separate masses are there. So we can see that the power of monomass 52.1 microwatt with 0.5 hertz bandwidth widening only, but separate masses 1 hertz bandwidth while 43.2 microwatt power. So this simulation confirms the feasibility of pacemaker enhancing lifespan of performance. Actually, battery lifespan is very short, so need very surgical operations, very frequent changing, so it is very discomfortable for the human beings. So if we change that battery, that lithium-ion battery and so on, that is a bulky and toxic, by this design, so that the energy harvester device can extract the energy from heart vibration and again convert it into electricity, and pacemaker continuous run with this combination, and pacemaker gives the impulsive signal to the heart when it goes down or goes very fast. So that this is a result of conclusion of my work. Simulation confirms that the feasibility of pacemaker enhancing lifespan and performance. And in future, I want to enhance my work in the area that we use PVDF material only. We want to use composite material like some other ceramic components which are biocompatible, and some other piezoelectric enhancement material like yttrium and scandium is also can use over here, so that we can get a higher efficiency, higher output, higher voltage also. And also we include human biological fluid, and so we create an environment like a heart and in my console, and see the result what if a real world real things are there. So potential application is it is a self-powered pacemaker because no external battery is needed. It is a self-made, self-powered pacemaker. It is also used in neural stimulators, drug delivery system, wearable devices, and so on. So future improvement is there. Higher efficiency. If we want or more higher efficiency, reduce size, enhance reliability, and it also long term can be used. These are the references used in my paper. Thank you. Funding agency BST India, and I also want to thank my lab, VLSI Device Lab, IIIT Allahabad, where we use this software console 5.5. Thank you, sir.
Okay,
Thank
ma'am.
you.
Ma'am,
Yes.
there is a very
Yes, sir.
good work. You explain there is a two process. One is the separate mass and monomass.
Yes, sir.
Ma'am, which one is better? Because you show some result is 52 microwatt for zero point 0.5 hertz bandwidth, or some is 1 hertz bandwidth. Both are used for the same bandwidth or not?
Yes, sir. Actually, heart vibration is between 20 to 30 hertz. We want to take result only 20 to 30 hertz range. So both result are 20 to 30 hertz range, but there are some pros and cons both. Because if only we want power, there is no widening in monomass. Only 0.5 hertz widening we can see. The red one is monomass. So there is a small narrow widening. But when we get separate masses, we get enough widening over there because there are separate masses over there. Separate masses move according to their, so that the first, second, third, fourth, fifth, like that. When first resonance frequency comes from matching first cantilever moves, then second move, then third move, then fourth, fifth. So that if we want to cumulative graph, so that we can see a broadening of the frequency. So that's actually the pacemaker requires some already time span that he want to work. So he store the energy in a supercapacitor or rechargeable battery, so they can use further. So because it pacemaker gives impulsive behavior if only one frequency we get output, so that it is very dangerous for us. Beyond this frequency or lower this frequency, what the result if drastically zero. So we get some widening in separate masses.
Okay, ma'am, my last is which simulation tool is used for this simulation purpose?
Sir, COMSOL
Oh,
5.5 multiphysics in VLSI laboratory, IIIT Allahabad.
okay, ma'am. Thank you.
Yes, ma'am. Yes, sir. Thank you so much, sir. Thank you. Thank you.
Okay, thank you. You can say your unshare your screen. Next paper ID is 399.
Yeah, hello. Am I visible?
Not yet. Turn on the
Hello.
camera. Yes, you're audible, but you're not visible to us.
Now.
Yes, now you are visible. Okay, say your screen, PPT, and you have 10 minutes maximum.
Oh, sure.
You have,
Is it visible?
yes, it is.
So, good morning, everyone. My name is Sujal Bojani. I'm a final year BTech student pursuing electronics and communication engineering from Nirma University, Ahmedabad. I'll be the presenter today for our paper, Novel Iterative Non-Restoring Algorithm for Square Root Computation on FPGAs. So, other co-authors are Umang Fultaria, one of my batchmate, and Professor Sudhanshu Janvatkar. He's a professor at Nirma University. Okay, so introduction. Why do we need square root computation? Okay, that too in hardware. So like nowadays, square root computation are crucial in various applications. Either it be signal processing, image processing, or sensor fusion on in robotics. Okay, the implementation of information processing on hardwares such as ASIC and FPGA has seen a huge
Sujal,
demand.
sorry to interrupt you. For your first
Yeah.
slide is visible to us.
Okay, just
Put it in slideshow mode also.
yeah, it's already in slideshow. Okay, so now is it visible?
Yes, now it is visible to us.
Okay, so yeah. So a little bit of introduction. So the need of square root computing on and specific hardware such as FPGA or ASICs. So high speed data analysis has been become an huge demand for quick computation. Okay, so like in ASIC and FPGA, the increase has demand has seen a huge surge in research and R&D work for having a specific hardware to calculate specific equations or algorithms. Okay, so square root computation on hardware is a complex task. So due to its algorithmic nature, hardware requirements and time-consuming intermediate calculations. So this paper reviews key square computation algorithms, discusses a novel algorithm, and explores its hardware applications. So next slide. So, but why on FPGA? So FPGA offers fine and coarse grain parallelism, enabling system realization and on a single chip with a balance of power consumption and performance with cost. So the use of information processing algorithms on hardware like FPGAs is again gaining a huge popularity. So this algorithm will like help a lot in developing specific application specific ICs or application specific computation, which will actually improve the overall on a single chip information processing. Okay, so FPGA it offers hardware accelerations, it offers parallel processing, and everything can be integrated on a single system on chip. Okay, so next, a little bit of background. So the recent research on efficient square computation on FPGAs has emphasized optimizing computational efficiency, hardware resource utilization, precision, and energy consumption. Traditional algorithms like Tony Lishang's C-polar lemma are reliable but computationally very intensive, making them less suitable for real-time applications. And of polynomial approximations such as Taylor series expansions, they minimize hardware cost but may result in significant errors. So using a traditional algorithm is very hardware consumption consuming, and it won't be a actually what you could say, a better option to implement on hardware. Okay, traditional algorithms are reliable but computationally they are very intensive. They require a lot of power, a lot of hardware utilization. So implementing it in a hardware or a real-time system, well, it's very difficult. Okay, so we wanted to explore what are the different simple mathematical algorithms which can be implemented on hardware. So a few of them are guess and check algorithms, averaging, repeated subtraction, prime factorization, and long division. We have explored all of them and tried to find out their merits and demerits, and how can we realize any simple mathematical algorithm on FPGA. So here is a table comparing all the merits and cons. So out of all of them, a few were kind of practically possible to develop in hardware. So we've used a mixture of few of the algorithms, primarily long division algorithm to implement on FPGA. So our proposed algorithm. Our proposed algorithm is non-restoring because we are trying to predict the number of iterations required for calculation, and we do not require additional steps to correct or manipulate the intermediate results. That's why it's non-restoring. So it is based on long division process. We have an running accumulator which tests whether the current estimate by division is the closest to the root or not when it is squared, and if it is less than or equal to the radicand or not. Okay, so at each iteration
a new bit is appended to the root and accumulator, and it is updated based on the conditional subtraction. Okay, so we provide an input number, and left shift and subtract it from the square root, and try to iteratively repeat that process until we get the until the number of iterations we have decided has run out. So we are trying to predict the number of iterations to get the absolute accurate value of the square root. Okay, so the strengths of the proposed algorithm, why it is very suitable for FPGA. So it is bitwisely approach. So it is more faster and efficient as we are operating on 2 bits per iterations. So no more than 2 bits will be changed, manipulated, or worked on. And it's hardware friendly. Most of the arithmetic operations are either addition, subtraction, or shifting. The algorithm does not require any complex LUTs or complex other sub algorithms or other sub equations to calculate the square root. And here we are trying to predict the number of iterations. So it is very iterative convergence. So it guarantees a fixed number of iterations, and the output will be provided in a fixed number of cycles. So the algorithm's efficiency and hardware suitability makes it very ideal for high performance applications. Okay, so we had tested our algorithm on an Altair D2 FPGA. So this is the RTL view post synthesis, and these are the what do you call it, the evaluation or the hardware consumption we had observed. So the total number of logic elements consumed were around 1200, which is around 3% of the total logic elements available on the FPGA. And with a clock frequency of 50 gigahertz, we were able to calculate the square root in around 8 clock cycles. Okay, so that goes around 160 picosecond. So we were able to show an output in around 160 picoseconds or 8 clock cycles. And the total thermal power distribution was around 118.83 milliwatt. Okay, so our algorithm is like very less consuming in terms of hardware, and the number of clock cycles it requires is also quite a few compared to a huge or a demanding task, which might require a quick like a real-time system which might require a quick calculation. So this is the FPGA single tab logic analyzer waveform. This is the real-time waveform that we have observed on the FPGA. So for an input of 1024, the square root of is root 32, and the remainder is 0. Here it's a perfect square, so we were able to find the root perfect root. Okay, and for the next, the input was 53 with the square root 7 and a remainder 4. Okay, so what are the applications of square root computation? So applications can be like many for this design. Real-time systems like drones, autonomous bots, etc. can use this hardware square root algorithm. And for drones, it primarily can be used for video stabilization, in which calculating frame by frame displacement will be very helpful in a shorter duration of time. And for autonomous robots, pathfinding and obstacle avoidance relies heavily on square root computations, and this algorithm might be very useful for them to calculate the distance or path in real time. Okay, so next conclusion. So our proposed design operates with a high accuracy and hardware efficiency, around 1200 logic elements, and it's very quick. To be said, just 8 clock cycles are required to calculate the square root, irrespective of whatever the size it, either it be 8-bit, 16-bit, 32-bit. Okay, so by implementing this algorithm on FPGA or on hardware, we can design high performance applications like robotics, UAVs, drones, and even real-time signal processing. Okay, this algorithm speed and efficiency makes it a valuable asset in real-time data computation. And future works, what could we improve in our algorithm? So future works we can improve the fractional accuracy for large numbers. So for numbers of like 5-digit, 6-digit, 6-digit numbers, the square root may contain fractional inaccuracy if it's not a perfect square. Okay, so handling that might be what we could improve in our algorithm in the future. Incorporating error correction or error handling has not been done yet. We can still like add another algorithm or another process to compensate that, and we can further optimize in speed and hardware utilization by either using any parallel or changing our hardware in such that has to be explored. Other is designing a full custom ASIC implementation for any custom design, either it be robotics or any other digital IC. Okay, so that might improve the overall performance power area. Okay, so and last would be application specific. So our hardware our algorithm can be optimized based on whatever the requirement is. Based on the requirement, you can change the number of bits, the number of iterations, and you can get the optimal result, whatever your requirements may be. Thank you.
Okay, very nice presentation. In your RTL design, some algorithm is used. Which language is used? VSDL or Verilog?
It's on Verilog, sir.
Verilog. Okay. In your title is right non-restoring. Non-restoring means?
So here we are trying to.
Yes.
Yeah. So here we are trying to predict the number of iterations it takes to calculate the square root, and we do not require any additional steps to go back to the intermediate results and either correct it or manipulate it. So that's why it's non-restoring.
So how many iterations are used?
It depends on the width of the bits. So for 8 bits, it might be C2 log of the number of bits, width of the bits.
Okay. In your simulation results, you write 50 gigahertz.
Yeah, that was the internal clock frequency of the FPGA Altera DE2.
50 gigahertz. Okay. What is the hardware complexity in terms of LUTs, CLBCs?
Around 1200 for 8-bit square root computation.
Okay. You mentioned power dissipation. What about delay?
So we didn't have any much delay for our observation. We could say that as soon as the start signal is deasserted, we were able to get the output in 8 clock cycles.
Good. Thank you.
Thank you.
Very good work. Okay, thank you. Fine.
Okay, thank you. Thank you, Sujat. So next paper ID is 463.
Good
morning, madam.
Good morning. Turn on your camera. And share your ID proof. Okay, fine. You can go ahead, and you have maximum 10 minutes for the presentation.
The slide is visible.
Yes, it is visible to us. Put in slideshow mode.
Myself, Dr. Pramod Kumar Patel. My topic is cache memory for the design of high performance SM for transportation and logistic drone. These are the contents: introduction, objective of research, methodology, research, results, and conclusion.
Doctor, your slide is not moving, and your not in a PPT mode.
Okay, sir. Sir, it is visible.
Yes.
These are the contents: introduction, objective of research, literature review, methodology, and result and discussion, then conclusion. These are the this is the objective. Our fundamental requirement of cache memory in computer architecture and system, in which 60 SRAM is conventional, which is used for storage. The need of memory capacity per chip area is growing now, so we have need to demand of power. So there are some limitations in conventional silicon MOSFET devices. So we have required some alternative devices like CNT-FET, GNR-FET devices. So these alternative devices can further scale down, and we can reduce the power consumption, as well as we can improve the speed of the SRAM and processors. This is the basic GNR-FET device structure, which contains drain, source, and gate. Below the gate, we are using graphene nano ribbons to control the drain current, which significantly reduces the leakage current, as well as it reduces the power consumptions. This is the equivalent circuit of GNR-FET structure. These are the objective of research. Because SRAM are the core component of memory cells, so we have need to downscale it to reduce the power consumption, and as well as increase the speed of the processor. So there is alternative device CNT-FET is also available, but CNT-FET devices some alignment and transfer issues which can address significant concern. So it also reduces power consumption, delay, and read write, improve the read write stability. So we are using GNR-FET device. These are the literature review used to implement our proposed circuit. Graphene nanoribbon have a lot of potential for use in future nanoelectronic devices. Metal graphene nanoribbon is useful for low power and high speed memory circuit due to its low contact resistance. So it consumes less power as compared to the conventional silicon CMOS technology. Numerous papers have been published. So there are some methodologies to improve the performance of proposed cell. These are the methodologies. So first we have implemented our proposed SRAM using GNR-FET based circuit. So here we are using also a multi-threshold technique for the optimization of proposed SRAM, and we are also using device sizing ratio for reduction of leakage current, and we are using graphene devices due to its low resistance technique. This is the proposed 5T SRAM which is implemented using GNR-FET devices. In this circuit, we are using 5 transistors instead of 6 transistors as used in conventional silicon CMOS technology. Here, due to this 5 transistor, this significantly reduced the area of proposed SRAM, and this is can be used as bit line 1 and bit line 2 to which significantly improve the performance.
These are the results and discussion. Data retention voltage is very good in this circuit. Sub-threshold analysis we have done for the circuit. SNM for this circuit also improved. Read SNM and write voltage margin also improved in this circuit. Leakage power consumption significantly reduces, and read-write power consumption also reduces for the circuit, and read-write delays are also improved using this, and layout area is also significantly reduced by using this proposed circuit. These are the results we have using simulator HSPICE simulator. We find that for using supply voltage of 0.3 volt, data retention voltage is 0.16, and power dissipation is very less as compared to the conventional techniques, which is 8.16, and this we have reduced 0.18 nanowatt, and leakage power consumption is also significantly reduces in this. Mean read and write powers also significant improvement source. Area is very less as compared to the conventional silicon CMOS technology and CNTPT technology. This is 0.6 and 7 micrometer square. These are the some results, simulated results, which shows that our proposed circuit consumes very less leakage power consumption as compared to the GNRPT 60 SRAM and conventional 60 SRAM. It also shows the read-write SM also improved in this proposed circuit. This is the layout diagram for the proposed circuit. These are the conclusion. The low leakage 16 nanometer CNTP and GNRPT based 5T SRAM design is optimized using for drone technology. Actually, drone also uses the SRAM and processor. So these are battery operated systems. So SRAM low power SRAM can also improve the performance of that drone technology. In this operation, sub-threshold operation suggested 5T cell offers read disturb free and increase write ability. The proposed approach makes use of device size differences to the increased data retention voltage, and in compared to the standard 5T SRAM, the multi-threshold approach enables low leakage operation and sizable improvement in delay. This proposed circuit can be used in a future industrial scale fabrication of more intricate cache memory architecture can be built on the proposed cell. These are the references which are used to implement the proposed circuit. Thank you, sir.
Thank you, sir. As per your presentation, your main aim is to design a 5T SRAM using CNFET. Okay?
Yes.
Okay. So which software, which tool is used?
HSPICE simulator is used to implement the circuit, sir.
Okay. So how the layout is designed in HSPICE simulation tool?
Actually, these are designed in cadence virtue models, sir.
Cadence
HSPICE cannot be used directly in design the layout of the circuit.
Okay. In a conclusion, you say some multi-threshold concept is used for low leakage. So what is the concept of multi-threshold in your design?
Multi-thresholding means each device has individual thresholding voltages are different. So we can use these devices to control the leakage current for device sizing.
We agree. This is some conventional or some definition. Multi-threshold is used for the low liquid. But in your design, how the multi-threshold concept is used?
This is different for PMOS and NMOS.
You use some 5 transistor to design your SRAM. Okay.
Yes, sir.
So how the multi-threshold concept in use? How many transistor in PMOS and NMOS? Some different threshold value.
Yes, sir.
Okay. The last my query is, sir, some static noise margin for read and write operation.
Yes.
Please define which how the value of static noise margin for read and write operation.
Yes, sir. Read and write static margin has been improved. This is approximately 315 millivolt.
Okay. Okay, sir. Thank you.
Thank you, sir. Thank you, madam.
Okay, thank you. Next paper ID is 480. Sorry, 580. Miss Nutan?
Madam,
Yes, ma'am. Yes, ma'am.
Yes, sir.
ma'am, how many papers are left?
So this one is the last one.
Okay, okay. Thank you. Thank you.
Nutan, turn on your camera.
Yes, ma'am.
Turn on your
Yes, ma'am.
camera
I'm
also.
trying. Yes, ma'am. Is it visible,
And say
ma'am?
your ID. Yes, it is
Yes, ma'am.
visible. Say your ID.
Ma'am, ID.
Okay, fine. And Nutan, you have 5 to 8 minutes because we have next keynote talk from 11:45, right? So please complete
ma'am.
your presentation within 8 minutes, 5 to 8 minutes only.
Okay, ma'am. Ma'am, is my screen visible in slide mode?
No. Put in
Okay.
slideshow mode.
Okay, ma'am. Okay. Now, ma'am, is it visible
Yes, it
in
is.
slide mode?
Yes, yes.
Yes, yes, it is.
Oh, a very good morning to one and all present over here. Today I'm going to present my research work on the topic.
Yes.
This is the design and analysis of an operational transconductance amplifier for biomedical system and its application in low pass filter for ECG signals. So I'm Nutan. I'm a research scholar in EC department of NSUT College, and this is my paper ID, that is 580. So coming to my introduction part, there has been a technological advancement in integrated circuits over the past few years, and because of that tremendous growth in the IC technology, there has been a reliable operation and portability added to biomedical signal processing. So because of that, many power efficient systems are present in biomedical era. Field. So we have, as we can see from the table, there are a few biological signals with their frequency range and amplitude. So my work is based on these ECG signals that ranges from a few microvolt to millivolt, and the frequency range up to 250 hertz. So because for that to process such a low voltage and low frequency signals, the amplifiers are used to before processing it to the digital signal processing part. So we have selected an OTA, that stands for operational transconductance amplifier, and that is used for biomedical instrumentation system along with the sensors and implants used for processing the biological signals. It is the key element in realizing the GMC filter and GMRC filter. So in my work, I have presented an ultra low voltage, ultra low power current mode operational transconductance amplifier with very high CMRR and FOM. So FOM is basically a criteria to measure the performance of a design. So FOM stands for the figure of merit, that basically tests the energy efficiency of the design. So, in the past, coming to the literature survey over the past work that has been reported on that topic, there has been some low voltage OTA architecture that are presented in the references 2 to 9. So, because to gain the low voltage operation, that is mandatory because of the portability and longer battery life that is needed for implants and the other biological signals and for biocompatibility. So we have the number of designs that are based on the bulk driven MOSFET. In bulk driven MOSFET, what we are doing is we are setting the input to some bias voltage to have some channel. Basically, the MOSFET is biased with, and the gate is biased with a channel. Bias with a fixed voltage to establish the channel, and input is provided to the bulk terminal. So this is basically a very low low voltage. This allows a low voltage operation, and it basically mitigates the threshold voltage limitation that coming in the path of the input signal. And but the drawback is it has a high input referred noise that is not required in case of biomedical signal processing. We need to make it as low as possible. So other options are we have used gate-driven options, gate-driven MOSFETs, but they have the problem of the swing. That is, the input signal has to overcome the threshold voltage. After that, the signal is being passed. So there is a limitation in the swing range. So we need an amplifier for high gain and high CMRR to reject the noise that has been captured by the system for system that is used for amplification. And low input referred noise, again, the input referred noise signifies that the flicker noise is reduced and the amplifier is a efficient one. So the problem formulation is, first of all, we have to mitigate the effect of threshold voltage. We have to ensure low power consumption, and for designing amplifiers, and we need high gain in the frequency range up to 10 kilohertz and low input referred noise. And alongside, we have the range of signals from microvolts to millivolts. So linearity is a must-have factor. So in the proposed design, what I have used is I have designed the OTA keeping in mind the biomedical application, and one such application of a low pass filter. That is a fifth order low pass filter is designed using this OTA for ECG signal processing. And to ensure the ultra low voltage and ultra low power operation, I have operated my OTA in the sub-threshold region. In sub-threshold region, what we have is we have the power efficiency. Why power efficiency is measured in terms of GM over ID in case of MOSFET, and in sub-threshold operation we have maximum GM over ID, and because of that we have energy efficiency and ultra low voltage operation. And because in biomedical signals we don't need very high frequency range, up to 10 kilohertz is sufficient. So sub-threshold is an advantage in case of biomedical signal. Again, for the efficiency enhancement, what we have used is I have used dynamic threshold MOSFET. In dynamic threshold MOSFET, what we have done is we have basically the body of the MOSFET is biased. Body of the MOSFET is biased to the gate terminal of the MOSFET. So whenever the signal comes, the OTA conducts, and whenever the signal is not there, the leakage current is minimized. The device returns to its standard threshold voltage. And to enhance the efficiency, we have the partial positive feedback that not only gives the high GM and high gain, and alongside it gives improved frequency range. And to ensure the linearity, linearization technique, that is source degeneration, is used using the MOSFET. That basically gives reduced area and low power consumption, because we are not using the registers. So this is the design that I have been using and designed. In this case, the M1 to M10, excluding this M7 and M8, are implemented by DTMOS transistor, and the M9 and M10 are the partial positive feedback transistors. So in this design, what we have attained is the GM, the total transconductance, is given by this, and the DC gain and the resistance, output resistance, are given by equation 2 and 3. So what we have achieved is I have operated my design on plus minus 2.25 volt, and the power consumption of the OTA is 22.06 nanowatt. That is very advantageous in case of the biomedical application. And I have used the tool Cadence for the simulation purposes, and these are the AC characteristics that my design is offering a single stage gain of 50.38 dB with a frequency range of unity gain bandwidth of 11.71 kilohertz, alongside the CMRR that is 151.69 dB, along with the PSRR of positive and negative side are 98.22 and 50.44 dB. So coming to the DC characteristic is shown in figure 3A, and the ICMR that is input common mode range shown in figure 3B. The design offers a very good input common mode range and the linearity for the desired range. Next, coming to the transient response, that is showing the slew rate performance in figure 4A, and the slew rate of this OTA is 4.14 volt per millisecond and 4.17 millisecond. So that the slew rate is basically we don't need very high slew rate in case of biomedical system, because the time constants, that is tau is equal to RC in case of biomedical system, that is that has to be kept very low. The very high slew rate is not required in case, and along with we have given the load fluctuation response in 4B. Then coming to the robustness of the design, along with for the process corner, the supply voltage fluctuations and the temperature variation. So the circuit is very efficiently performing in these against these variations. And coming to the Monte Carlo simulation, showing the process and the device mismatch analysis. And I have run this simulation for 300 samples, and we can see that the circuit is the design is offering very efficient performance under this Monte Carlo simulations also. And as a design application, I have designed a Butterworth low pass filter of fifth order using this OTA as a main element, and the resistance and capacitors are used of equal value. And the whole low pass filter is basically giving the power consumption of 66.06 nanowatt, and the filter cutoff frequency is 250 hertz. That is suitable for ECG signals. So coming to the comparison with the relevant work, my design is basically working in very low power consumption, working with very low power consumption with high DC gain compared to other, and also the CMRR of the design is very good compared to others. And as we can see, the FOM of the design is best among the others, excluding this reference 7 that has been using the 2 stages along with the some enhancement techniques that is increasing the power, the area of the design. So coming to the conclusion part, I have presented a very low voltage current mode OTA with high gain, high performance, and low noise, low IRN noise, and high CMRR with improved linearity. And I have chosen subthreshold and DTMOS to ensure ultra low voltage operation, partial positive feedback, and the GM enhancement is used for enhancement of the performance, and the design can be used for designing other ultra low voltage, ultra low power analog filter and oscillator circuits. So including the future work of the design, this more application using this OTA can be designed. It can be used in EEG and EMG signals processing, and along with for EEG and EMG signals, we need a slight bit higher slew rate. For that, we can improve this design. So these are the references. So any questions, sir?
Thank you, ma'am. My one and last question, my query is, define dynamic threshold MOSFET.
Yes, sir.
You use some dynamic threshold MOSFET. What is the concept of dynamic threshold MOSFET?
Sir, in case of dynamic threshold is what we are doing is, sir, let me show you. Sir, in case of dynamic threshold, what we are doing is, suppose I'm talking about this M1. So that in that case, the body is connected to the gate terminal. So what we are doing is, in case of analog, what we are requiring is, we need the low leakage current. That means if the signal is not present, we don't require any noise or something to come in the picture. So the threshold voltage is at low value when the signal is not present, when the input is not present. But when the input is present, because this input is driving this body of the transistor also, so what we are doing is we are forwarding the body effect. So in case of forwarding the body effect, the threshold voltage is reduced, and when the threshold voltage is reduced, the circuit is able to work on the low value of the signal. So the circuit is turned on at low value. So this is a low voltage operation, low voltage technique that is used for basically reducing the threshold voltage effect.
Thank you, ma'am. Thank you.
Okay.
Okay, thank
Any
you.
further questions, sir?
No more questions.
No.
To find the paper presenter, I would like to thank each paper presenter who presented their paper on their hard work. It was really a fruitful experience. I would now request Dr. Richard Sharma to present to make a certificate as a token of gratitude and appreciation for being the session chair. Thank you so much, sir. Your presence really lifted an entire session.
Good afternoon. I
Thank you
managed to
for sparing your
connect.
valuable time. Thank you, sir.
Thank you, ma'am.
Your words were both inspiring and informative. Thank you, sir, for being here.
Thank you.
Okay, thank you, sir.
Thank you. Thank you, ma'am.
Thank you so much, and apologies. I tried to connect via Teams and finally managed to connect via Zoom. So do we still have a bit of time? Because we are running late.
Okay, good morning, ma'am. Hello, ma'am.
Good morning, hello.
A very good morning to one and all present. I'm Radhika on behalf of Electronics and Communication Engineering. I'm at the School of Entertainment Technology. I'm at the University of Uttar Pradesh. It's honored to welcome you all on the second day of WET International Signal Processing and Integrated Conference in 2025. I also wish to extend a warm welcome to all the delegates and the representatives present here. It is our great privilege to have very of two podcasts. I'd like to invite Dr. Richard Sharma to present a startling to Dr. Hi,
Thank you so much. Thank you so much for this opportunity and for the invitation. Let me just share my slides. Can you hear me?
Yes, ma'am.
Oh, that's good. So these are my slides. Can you see now my screen?
Yes, ma'am. It is visible to us.
Okay, that's really good. So how much time do we have?
30 minutes.
20. Thank you. Okay, so I would like to share with you some of the recent results that we have with my team on enhancing autonomy with Gaussian process methods and computer vision. And I would like to discuss, first of all, what are the areas of interest and the challenges. And then I would like to discuss mainly data-driven machine learning methods for autonomous data processing and autonomous systems. And one method that is especially powerful, one big group of methods, is kernel methods or Gaussian process regression. And I would like to show you recent results, how we introduce learning, especially of their hyperparameters, and how we design the kernels. And in the second part of my talk, I would like to discuss methods that we have been developing for wildfire detection and localization with uncrewed aerial vehicles, which is especially important after so many fires recently both in Greece and Los Angeles. At the end, I would like to summarize key points of the findings and future work. So our motivation is to introduce autonomy in different systems, like human-robot interaction in factories, where the operations need to be performed safely, and also we need some level of trust or trustworthiness in the developed approaches. And also outdoors, there are many operations, including delivery via drones of medicines and fire detection, just to name a few. And we consider, as I mentioned, especially a big group of kernel-based methods, the Gaussian process regression, where we use the method as a representation, as a tool to represent complex phenomena, including to track objects of interest, and we can represent complex probability density functions, as you can see here, this very complex shape, and then we can also quantify the impact of different changes, such as noise in the measurements, such as other kind of environmental factors. So the second type of using this method is to quantify the impact of uncertainties. And we have combined it with different kind of neural networks and to solve a number of problems. Just to summarize briefly the main ideas of the method, I have put this image where we have measurements. The observations are those red points, and then we have the ground truth, which is the blue solid line, and then with the method we can do predictions, and then at the same time the value is we can evaluate how accurate is the result thanks to a confidence interval like standard deviation, which comes inherently with the method. And it is a Gaussian process is a stochastic process which defines a distribution of possible functions that fit a set of points. And the method has an advantage to be able to work with a small number of points. So when we have sparse data, and then we want to do predictions as well. And it has been widely used in cartography, for predicting maps, and for other kind of tasks. And it has not only a Gaussian kernel, but then it has Matten, uniform, periodic kernels. And here, as you can see, we have the exponential kernel, we have these measurements, and the dependence between the input data and the function can be nonlinear in general. And then we can do quite good predictions, and our confidence regions are also quite important, especially, for instance, if we have a monitoring task under lighting conditions that are changing or other conditions, we know when we can rely on this method and on the solution. The method requires training, and as you can see here, we have the data, then we have the training set. F is the unknown function value, and then the training can be done offline or online. And then with the help of the kernel, we update it, and then we have the estimates, for instance, for tracking a vehicle on the ground. And we can represent with a kernel different type of measurements, different type of representations. We have the prior, which if we have a Gaussian distribution, then this is our Gaussian prior. We can work how to represent the covariance matrix. And then we have the posterior. And one key aspect is the optimization of the hyperparameters of this method. Normally, we have the expectation maximization algorithm, which optimizes the likelihood function L. And it can be done also online, as we have done in this work, published in the Journal of Selected Topics of in Signal Processing, where we actually subdivide the measurements, and we have a product of measurements, a product of likelihood for the subsets of measurements, and then we can represent the mean and the standard deviation. So the method has scalability aspects if we consider all the data, or if we consider high dimensional covariance matrices. But with this type of divide and conquer approach, we can overcome these challenges, and it works really well. Even with high level of noise, here you have results from tracking a vehicle on the ground, and then we have the sensors. The red dot is the sensor, and the green is the circle, which is the sensing range for every sensor, and then we have the uncertainty ellipses. And we have results with different level of noises and for different trajectories. And as you can see here on the left, we have distributed point tracking with clutter and without clutter as well. The method works well in both cases. Then we have been studying and developing different approaches with different kernels. There is a lot that can be done still in that direction. We have commonly the squared exponential Matten kernel. And the key question is, how do we introduce learning in those methods? And offline, it's clearly known how to do that, but online there are different ways, and one way is with the Windows-based approach with the expectation maximization, or recursively with a Kalman filter, with a particle filter. And recently we found also that combining with deep learning methods with convolutional neural network, we can build also a deep kernel framework where whether a convolutional neural network or purely an artificial neural network can also give quite good results for the learning of the hyperparameters. We have also introduced the high level of efficiency for real-time tasks, thanks to factorizing the kernel of the method. And one way is with QR factorization, or for when we have a lot of data, we introduce hierarchical off-diagonal low-rank factorization. As you can see here, we start with a dense matrix, but then we subdivide it into sub-matrices, and we can apply this process several steps. We normally have done it up to 10 steps, because when we introduce sparsity in the covariance matrix, this means we reduce the amount of information we have for the update. So it's a trade-off between how we introduce sparsity in this covariance matrix, and we have reported it in a range of works. This is one of them. And we have proposed methods where we represent both the temporal changes and the spatial separately. So we have a factorized kernel. And here you can see results for tracking of the same object, where we have a product first of the sum of kernels. They represent the spatial part, and then we have the Matten that represents the temporal part. So we are using in this case, signal strength data, which are from a network, from a mobile station to monitor the movement of the car. And we have the squared exponential kernel, which represents the flat area, but then we have the exponential kernel, which represents the useful information in the signal, the peak. Then we have the constant kernel, which represents noise. And then we have the temporal changes with the Martin kernel. And here we have implemented some of our algorithms in something called Stone Soup platform, which is a collection, collection of algorithms, a repository where there are different algorithms for detection, for tracking, and they are with different types of data. They can be sonar, LiDAR, radar. It is an open source repository which is available on GitHub. If you are interested in, you can see the resources. And it is a really good repository, open, where we compare working approaches in the area. And as part of the Stone Soup algorithm, we have implemented both the distributed and the centralized version of the Gaussian process method I'm discussing with you. These are some of the associate connected papers. We have sensors, a network. Then we have states that we want to estimate, and with historic data and online data, online measurements, we can represent different kernel functions, learn them with the maximum likelihood, and also with some deep learning approaches with TensorFlow, we can also learn the hyperparameters. And then we can represent the posterior in a distributed and centralized way and predict. So it's a really useful tool and repository. And then these are some results with that's nearly uniform motion, as you can see. Whereas here, this is for UAV, where we can have the areas of sensing from the sensor, and we can have more nonlinear type of motion as well. So when learning the hyperparameters of the method, we have considered another application for mixed traffic, where we have both human-driven vehicles and autonomous vehicles. And then the autonomous vehicle can estimate the speed of the vehicle in front of it and then adjust its driving. So it is quite an interesting task, and there are a number of works on it. So we have been looking at different case studies where we have a single ring, as here, or double ring. And then, as you can see, the red vehicle is the autonomous vehicle. Then we have the observed vehicle, the blue. So the red vehicle can observe the speed of the vehicle in front of it, estimate it with the Gaussian process method, and then adjust its control. And the interesting bit here is a multi-object system where there is a need of both estimation and control for this type of multi-object systems. So I'm not going to go in detail, but we have here just a very simple perceptron neural network which estimates the kernel hyperparameters, and we have a spectral mixed kernel which is suitable for this task. And we have updated the parameters of the kernel. We have estimated it in this way, and we compared with the maximum likelihood estimation method, where the state is the acceleration of the vehicle in front of the autonomous one, the velocity, the distance to the vehicle in front, and the delta is the difference in distances, and then the output is the velocity. Okay, and here we have a little bit more about the formulation. We have a deep kernel learning with different layers of the network. We learn both the hyperparameters and the weights of the network. And I think here we have some details about the experiment, where we have 19 vehicles, and these are the training data. These are the noisy speed data acquired within 600-second time interval. And then these are the results. On the left, with the red color, we see the results with the generic Gaussian process method, and the area is the red tube area is the standard deviation. That's the confidence which we have in the estimates. Whereas on the right is a result which we have after learning of the hyperparameters of the kernel with this perceptual neural network. And what we demonstrate is actually that because the neural network can extract features in a better way, then we can have better results than the maximum likelihood estimation. And here we have more information about the efficiency, where we have the deep kernel, the Gaussian deep kernel learning Gaussian process, conventional, and the training takes longer. But once the algorithm is trained, then with the deep kernel learning in real time, we can have even quicker performance than if we were to use a window-based approach or the traditional Gaussian process. So there is quite scope to continue in this direction. So we have been looking also at solving autonomous tasks in with electro-optical video data and with thermal data. And one of them is when a UAV is flying and collecting data and wants to detect autonomously where the fire is on the ground. As you can see, fires have quite changeable shape. They change their color quickly, and most of the models face difficulties in representing these dynamics. So we've been looking at developing dynamic novel learning color models, texture, and combination of them, including motion. And there is a range of methods from random forest trees to wavelets, local binary patterns, histogram of oriented gradients to convolutional neural networks, including you look only once, different versions, but now YOLO 8 is one of the most advanced in this stage. So with the wavelet-based algorithms for fire detection, we have first an extraction of some properties. We've done it both for texture and for color. Color, normally we represent it with a histogram, but we can use wavelets to represent this changeable pattern as well. And then after that, we apply morphological operations, wavelet transform, Dalbash's wavelet transform, or discrete wavelet transform. Then we can use energy maps. And then with the help of the energy maps, we can select those channels of the color space that are most representative for this changeable pattern. And then with the information from the wavelets, we can see the different energy components and then make a decision, is it part of the color area or not. And here you can see a representation of 3 different methods. One is with more adapting the red, green, blue color, and also we've been experimenting with YCBCR color space. And then this is a classifier based with the light gradient boosting machine. And the one which actually surprisingly gave the most accurate results is the YOLO 8. And the accuracy varies. It depends on what kind of videos we have, but it can achieve 90% in some cases, in typically around 70. YOLO also requires a lot of training. That's something to consider. And we have been working with thermal data. If we don't extract the pseudo colors, then we have something, as you can see on the screen, which is more like grayscale videos, and those are not containing the full information about the temperature changes. So we are working still on the thermal video aspects, how to extract the radiometric information, because not all UAVs provided, the cameras that are coming jointly with UAVs provide mainly the pseudo colors or grayscale, like videos like this one. So you can see here the actual color. This is from one of our tests. And then on the right is what the algorithm extracts, and then this is part of another result from real trials. And YOLO, as I said, it also recognizes smoke. Smoke is much more difficult to detect and recognize, especially from different angles of view. Whereas the algorithm with YOLO 8, the result is reasonably accurate for both. And we are continuing in this direction, and also to combine both thermal and optical results. As you can see here, that's the probability of detecting smoke and the probability of detecting the fire. And that's a UAV which is actually dropping water to tackle the fire. And I think we have also results with one of my previous students, where we combined convolutional neural networks with the optical flow methods. And we have Gaussian mixtures, which represent the dynamic changes in the color of flames. There are interesting things in this combination, because with the optical flow methods, we can detect the region of interest, and then we can track it, whether with a Gaussian mixture or Dirichlet process mixture of models. And we can deal with large and small volumes of data. And then combined with a swarm of UAVs, we are focused on monitoring an area of the fire, such as if you have 1,000 kilometers squared, then the UAVs, they have to optimize their path, you can think, and then find the location in both in image coordinates and in physical coordinates. This is one of our previous works for optimizing the number of vehicles, and also linked with their energy. So it is an optimization and path planning task. I think that's all I prepared, and thank you for this opportunity. I discussed with you mainly the data-driven methods that we are developing, and we have compared some of them with model-based approaches. And then the main thing is solving several problems for autonomy, but at the same time, we are interested in when are these algorithms working well, when are they resilient to changes, to measurements, to environmental conditions, and then solve scalability aspects with different factorization methods and improving the efficiency. And in our case, we've been using the variance as an indicator about the trustworthiness of the algorithm. Small variance, this means high level of accuracy, and high variance is the opposite. And one way to enhance the efficiency is to work with digital twins. We've been also considering, we have the human-robot interaction case study, the transport systems, and others. And these are some of my support organizations. Thanks everyone to my collaborations as well. And thank you for the opportunity. That's me.
Okay, thank you so much, ma'am. Any questions from the audience?
Yes, ma'am. There's a question from the audience here.
Okay.
What are the potential benefits and challenges of using the Gaussian process methods in real world automation system?
What are the challenges and the benefits? The benefits are that, as I said, it's a method that can work with a small amount of data. It can work when we have sparse data. And initially, it has been used to create maps in cartography when we didn't have such amount of data. We could predict even with a small number. So in contrast to deep neural networks, where we need a lot of data for training, this method has the opposite characteristics. It's not so demanding to data. That's one. The second advantage is we have the covariance matrix, or some of the parameters of it. When we learn them and propagate them together with the estimates, then we have information about the accuracy inherently. It's not only the covariance, but also there is an evidence lower bound, which can indicate to us, is the method working well or not. And also it can be implemented easily in a distributed way. Disadvantages, we are introducing efficiency, as you have seen, with factorizations or with in a different way, because if we have to invert this n cube matrix n by n and by n, so n cube, that's because the inversion, that requires more computational resources. And I think that's pretty much. Otherwise, it's quite flexible, and there is a scope of learning. It's a non-parametric method where we don't need an exact model. For tracking purposes, there are many methods that rely on accurate representations, accurate models, whereas in this particular case, we are working in a more generic way, in more generic settings. Yes, these are the main ones.
Okay, ma'am. Thank you.
Thank you, ma'am, for being here. We wanted to express our heartfelt thank you for your participation in SPIN 2025. Your talk was both inspiring and informative. Thank you, ma'am, for such an informative session. Also, we would like to present a certificate to ma'am.
Thank you so much. Much appreciated. And Yeah, good to see you all.
Thank you so much, ma'am, for sparing your valuable time. Thank you so
Thank
much,
you.
ma'am. On
Thank
the behalf
you.
of Amity University. Okay, thank you.
Cheers.
Bye.
Thanks. Bye.
It is a great privilege to have Dr. Sumit Bharadwaj with us today. I would like to invite Dr. Richa Sharma to present a sapling to Dr. Sumit Bharadwaj. Dr. Sumit Bharadwaj is a seasoned professor with PhD in electronics and data science. He holds a BTech and MTech in electronics and communication. Dr. Bharadwaj specializes in signal processing, MATLAB, Python, data mining, AI, and machine learning. In 2022, he was awarded a prestigious postdoctoral scholarship from Sweden when he conducted advanced research in data science and analytics in the field of genetics. With extensive experience spanning both academia and industry, including teaching roles at Amity University, GD Goenka University, and various MNCs like Citigroup, Dr. Bharadwaj has a strong background in research, innovation, technology development. Also, his work includes 30 plus publications, multiple patents, and authorship of international books. He also serves as a reviewer for several esteemed international journals. Welcome once again, sir. Sir, would you like to call upon the paper presenter or would you prefer if I do it?
Thank you, Radhika, for such a great welcome. And it would be great if you can, call their names.
Sure, sir. Thank you. Now, I would like to call upon the paper presenter ID 277 to present their paper. Thank you. Also, keep the paper presentation limited to the 10 minutes time span.
Good afternoon.
Okay, fine. It is visible to us. You can say your PPT.
Do you hear me?
Yes, it is visible.
Can I start?
Yes, please.
Thank you. Hello, good afternoon. My name is David Shapiro. I'm from Samara Research University from Russia. And I want to present my work, a method for synthesizing test videos based on the evaluation of the autocorrelation function. On the slide, a description of my work is presented. First, I will explain why synthesized video is needed and what the requirements for the synthesized video algorithm. Then I will provide a description of the mathematical model of video, and model describes parameter estimation for piecewise constant component, texture component, and estimation of video intensity. At the end, I will show the final result and demonstrate it using graphs. Testing video requirements algorithm requires a large dataset because video vary in brightness, spatial features, and dynamics. Finding and storing real video is time consuming and resource intensive. Instead, using synthetic videos with adjustable characteristic is a faster and more efficient solution. Requirement for algorithm is demonstrated by this slide. The main is the ability to quickly generate video with characters similar to existing ones and low computational complexity of algorithms. Description of the model. The model needs small parameters because people can easy to make this model, and I suggest model with 5 parameters, 5 component models. What is it components? It's a pseudo M mosaic is a pseudo random 2D mosaic field representing the stan. It's regenerated with when the stan changes. And texture component for random brightness is a stationary random field with zero mean, set variance, and pixel correlation. It stays the same between the stan change and regenerated afterward. And to noise, texture noise and sensor noise. Texture component unchanged until the next stan, and the sensor noise caused by physical effects in the camera. It changes randomly in both space and time, regenerating for each frame. And it's parameter of frame, and time parameter for video is stand change intensity, lambda. Its parameter controls the simulation of editing counts in the real video. And estimation of model parameters, spatial and temporal autocorrelation function were used for estimated parameters. A more accurate approximation of the image autocorrelation function can be achieved using a B exponential model with 2 independent noise components. The formula is shown on the slide. Since the synthesized image is assumed to have isotropic statistical properties, we will analyze only one cross section of the ACF. Therefore, final formula this on the slide. This graph is example of real video, 3 real video, real bar, salute, Gaia, and road. Description of this video will be later. Estimation parameters for mosaic for x non-zero, only first 2 terms in this formula are non-zero. This means the autocorrelation function is the sum of 2 exponents, fast exponent and low exponent. Fast exponent is describe mosaic component and texture components, and slow components describes texture component. From this graph, it's clear that the argument increase. The fast exponent stabilization happens from 50 to 100 others, and this parameter is parameter of correlation rho m, and we now rho term, the variance d term can be determined experimentally. Estimation of parameters for texture and noise. Okay, I can say that texture components evaluate similarly like mosaic components. And the remaining two model parameters, the noise variance, and sensor noise and texture noise. To separate these values, multiply frames need to be analyzed. By comparing the corresponding regions in consecutive frames, the difference are caused only by sensor noise. The variance of the difference between two such frames equals twice the sensor noise variance. The variance of texture noise is then calculated using the other model parameters. On the slide, frames of real video, which used in this research, it's a football match, it's a dynamical musical clip, and a road video. Based using the estimated values of each component in expression, we created an autocorrelation function that approximated the average frames on three test videos. Three test videos was presented on previous slide, but these plots of the ACF. The figure shows the individual ACF components and the final resulting graph. And when moving from frame synthesis to video synthesis, a key parameter is the stand change rate. Stand change happen randomly at discrete times, and each pixel changes a piecewise constant function with independent values. Following a stationary generalized telegraph signal model, the autocorrelation function of the signal is also exponential, similar to average of frame. By estimating the correlation coefficient, we can calculate the stand change intensity on this formula on the slide and the example of this real video. The table shows the estimated video model parameters which can guide the generation of synthetic test videos. To create a diverse dataset, experiments should explore a wide range of parameter variance as listed in the last column on the table. Based on the obtained ACF model, the texture component can be generated separately using the spectral synthesis method. The resulting texture will represent a random stationary field. The model's input consists of the ACF field and white noise field with the unit variance. Example of texture on the slide. And mosaic synthesis, the study describes algorithms that enable the creation of a pseudo-random piecewise constant image based on specified variance, mathematical explanation, mean, and correlation coefficient. These two images of characteristic similar to this real video, the image differs visually from each other but retains the same spatial and brightness statistical characteristics. Conclusion: the study presents the method for synthetic video with specified parameters. When all model parameters are available, it's possible to generate video with characteristics similar to the original. Synthesized video can be of any generation. The synthesis process does not require significant time, and drawback of this method is enables it to simulate the movement of real objects. The proposed model is recommended for preliminary experiments only. Thank you for attention. Question?
Hello, Dr. Sumit.
David, it was a great presentation, and I hope so I'm audible, right, David?
Sorry,
Yes,
please.
you are audible.
Okay. So, David, my question is about from the presentation. First of all, that this technique, it is, can we apply this to generate deep fake videos?
Uh, y- Deep videos. This technique can I use this technique on my researches with protection of the videos, and this technique can use in the machine learning algorithm with special character where special characteristic is important.
Okay. Any kind of special noise to which this technique is somewhat immune?
Sorry.
Your slide number 2. There you have
Is white noise or it's a noise uncorrelated. Only first x 1 second.
Okay, and any specific data set means what kind of data set you use to validate, your this approach of video synthesis? How have you done your validation?
I use data set from internet, but this algorithm is universal and more large data set I can use for more diapason of parameters of my algorithm. Of course, if I use more videos, this accuracy of evaluation more high.
Okay, that's it from my side, Richa ma'am. Thank you, David.
Thank you.
Now, I would like to call paper presenter ID 294 to present their paper. And also, please keep the presentation between 7 to 8 minutes time span. Thank you.
Kajal, please share your ID. Any ID proof if you have?
294. Yes, ma'am. Should I show, ma'am?
Yes, in front of camera you can.
Okay, wait. Ma'am, is it visible?
Yes, it is visible. Yes, fine. It's fine.
Is my presentation visible to the screen?
Yes, it is visible. You can start your presentation. Put it in slideshow mode.
Good afternoon, everyone. This is Kajal, and I'm going to present my research paper titled Precise Lung Segmentation Utilizing Unit-Based Methods and CXR Images. So these are the contents that I'm going to discuss within the slides. So here goes with the introduction. What is first I discuss what is the importance of AI in medical image processing. So medical images require lung segmentation to evaluate and diagnose pulmonary diseases properly. So lung region segmentation is vital for the medical applications involving clinical tasks such as diagnosis therapy, planning, and prognosis assessment. Due to the remarkable process of deep learning algorithms, many researchers have used the automated lung segmentation methods to segment the lung regions. So multiple deep learning approaches for medical image segmentation were utilized, such as unit, pre-trained unit, or attention-based unit, or ensemble-based unit. So in this, there are various challenges that are there in manual examination of the lung segmentation. First, that is inconsistency in disease differentiation, legal issues, time consuming, low quality images, human error, and limited accessibility.
doctor-patient ratio in remote areas is low, and high morbidity and mortality rate due to low access. So these are the various challenges that we identify in the manual examination of lung diseases. So there is a need of a computer-aided diagnosis system, that is a system that uses the AI in its technology. So CAD system is basically an integration of artificial intelligence plus computer vision. So with the help of CAD system, we evaluate the disease properly and efficiently. So here are the advantages of CAD system. First, it helps in mass screening program. Second, telemedicine and remote consultation along with predictive analysis for risk disease, electronic health records, and process huge medical reports easily and can assist the doctors. The main point here is that CAD system can't just replace the doctors, but it helps in assisting the doctors. It makes their task more easily. So these are the gaps and challenges that I have identified. First, diagnostic process is manual, it is biased and less effective. Second, image can be corrupted due to the presence of noise, and vague and subtle appearance is challenging. Second, next is diagnosis are limited by inter and inter observer operator observer wire, and the existing methods have low performance. So these are the motivations that that helps in the task of AI, that helps the use of AI in lung segmentation. First, there is an advancement of imaging technologies, machine learning, and artificial intelligence. Second, unavailability of proper medical facilities and rural remote areas, along with others. So these, as I have discussed, there are various advantages of deep learning. So moving towards the related work and objectives. So various studies in the research have worked towards the lung segmentation. For example, Pride et al. Use a pre-trained VGG architecture. You et al.
Sorry
Use the
sorry to interfere, Kajal. Can you just skip this? Can you come on to your work?
yeah. So for that. So this is the dataset that I have used. I have used COVID-19 QEX dataset. It is collected from. It is collected by the Qatar University. It contains three classes: COVID-19, non-COVID, and normal. And I have divided the dataset into training and testing sets with a ratio of 70 to 30. So total images are 21,165 along with their mask. So we have changed the image size to the 224 into 224 width and height, by adding the normal augmentation techniques like flips, rotation, and brightness. So this is the experimental design. For example, I have taken the input CR and use a different unit architectures. For example, I have utilized ResNet 34, Inception V3 based unit, and VGG 16 based unit, and then produce the predicted mask by training the model. So these are the various hyperparameters that I have used. First, I have used the activation function for leaky relu, batch size 50 I have used, and epoch as 35. These are the various performance measures: accuracy, precision, recall, F1, and Jacquard and Dice coefficient that I have calculated for the lung segmentation. These are the results. Basically, I have used three models and compared the results since UNET has two parts, encoder and decoder. So what I have compared is I have changed the encoder part of unit. In the first, I have used the VGG 16 as encoder. In the second, I have used the Inception V3, and the third, I have used the ResNet based encoder. So these are the results, and these are the predicted masks on the right hand side. The first column is CXR, original CXR image. Second is original mask as given in the dataset, and the third, fourth, and fifth columns are the results that have been printed utilizing these models. So these are the loss graphs that I have calculated using these different models. First is VGG 16 base, second is Inception V3, and third is ResNet base. So Inception V3 base unit model shows the lowest value of loss during the training and the validation phase. So in the conclusion, we have used pre-trained CNN, pre-trained unit architecture, for example, ResNet, Inception, and V3. So basically, we have tried to change the encoder backbone of the unit architecture, and in the future, we will try to use the ensemble of the various unit architecture along with the second technique of applying attention unit, or we will integrate the hybrid systems to improve the segmentation and the generalization of the model. So for the generalization, we can use multiple data sets also. So thank you.
Okay, Kajal, thank you for the presentation. Could you please tell me that what was the ratio of the patients who are having the lung disease and who are not having the lung disease from your data set which you have taken?
So actually, I haven't mentioned the numbers, but it's around 5,000 approx. 5,000 is of COVID and 5,000 is of non-COVID. Non-COVID includes viral pneumonia and TB also. And normal is just the lung images without COVID and non-COVID.
But the total is 21,000, right? 21,160. So out
Yes,
of it,
sir.
you are saying 5% were having disease and remaining
Sir,
15,
approx
16,000.
7,000. Yes.
No, but the sum is not giving us 21,000 then.
Sir, I'm just approximating. I will.
No, you can't approximate. If the data set is not balanced, then how come you have, applied all these accuracy procedure and all?
No, sir. In the starting, the dataset was not balanced, but the dataset which has been provided on the Kaggle, named as COVID-19 QUX, it is almost balanced. It is not a imbalanced dataset. The
Kajal,
ratio is very
do
minimal.
you know the meaning of balance and imbalanced data set?
Yes, sir.
What
For
is the meaning?
example, if there are three classes and one class, for example, COVID chest X-ray 14 data set, it has 14 classes. But one class hernia has 77 images and the other class has 3,000 and something images, or 5,000 or 80,000, 8,000 images. So that is imbalanced data set.
That is imbalanced data set, okay. And how many false negative did you get over here? The number of false negatives I am asking. You have done it on your own, Kajal, right? It should be on your test then.
So actually, I'm not right now recalling the exact result, but
Where is the feature engineering part? You have not mentioned that. What are the important features which you have selected?
sir, I basically worked on the segmentation of the lungs, not the features. I have used a pre-trained architecture. So pre-trained encoder part is extracting the features itself. Not I am not manually extracting the feature one by one.
Yeah, that is fine. But what are the features?
So, for example, the pre-trained for example, the architecture will be extracting the images like what is the boundary of the lung segment, lung mass out of, as we are training it multiple times. So, it basically extract the, for example, what is the boundary and something like that.
So how it is distinguishing between the lung cancer, or if someone, suppose there is a tumor, so how it is going to distinguish between them?
So for that, we have to do the infection segmentation. For example, in the other dataset, COVID-19 radiography dataset, we have also provided the infection segmentation part. So this is only the for lung segmentation. We are just extracting the lung images. For the task that you are saying, that for that we need the infection segmentation mask as provided in its second dataset part. They have provided with CXR images along with the lung mask and the infection mask for various multiple images. So for that objective, we need to use the infection mask also.
And which algorithm did you use to select the hyperparameters?
Sir, Bayesian optimization I have utilized.
Okay, thank you. That's it from my side.
Thank you, sir. Now I would like to call paper presenter ID 427 to present their paper. Thank you.
Kajal, please stop sharing.
Hello, good afternoon to all. Hello, sir.
Good afternoon.
Ma'am, this is my ID. Is it visible?
Okay. Yes, it is visible to us.
Okay, thank you.
Share your PPT and you have maximum 8 minutes.
Okay, ma'am. Okay. Hello, ma'am. Is it visible?
It is visible, and please turn on your camera also, no?
Okay, okay, okay. Okay. Ma'am, my slide is changing.
Yes.
Yes, okay. Good afternoon, all of you. I am Akanksha Dikshit from IITDM Jabalpur, and my topic for today's presentation is sequential feature selection integrated with ANN for efficient detection of ALS, that is amyotrophic lateral sclerosis. It is related to muscles problem using SEMG signal. SEMG is a surface electromyography signal. These are some outlines which will be discussed by me. Okay, now introduction. This
Sorry
work
to
basically
interrupt. Can you please
based.
full screen it?
Okay. Is it visible now in full screen?
Yes, it is.
Okay, okay, okay. This work introduced a machine learning based approach for detecting ALS. ALS is amyotrophic lateral sclerosis. It is a neurodegenerative disease, which means that it affects the nerve cells, motor cells, and over time it affects the muscles. It becomes less active and weak. SEMG signals are used to detect ALS by measuring the electrical activities of muscles. Basically, SEMG signals are used to detect the signal frequencies range variations, for example, power and high frequencies. ALS often affects high frequency components. It is a progressive, means it gets worse over time. Muscles becomes smaller and less active. This is my data set. Okay, I have used N2001 EMG lab dataset. It is from 2001 year. The electromyography signals were sampled at a frequency of 24 kilohertz, means in a 1 second there are 24,000 samples are recorded for 11 seconds. So we have 151 signals for normal patients and 151 signals for the ALS affected patients. So total 302, and if we count the total number of samples, then we can calculate the 302 into 11 seconds, because 202 per second. So we have 302 multiplied by 11 seconds data, the total samples we have. We have the examples of ALS and normal SEMG signals. Here 10,000 samples for both the signals are tested. Okay. This is my proposed work. Here I have used the raw SEMG data for ALS and normal signals both, and total 40 features I have extracted from those raw data. These 40 features are EWM, MAV. These are the, suppose the wavelength, enhanced mean square value, zero crossing, skewness, kurtosis, these all. I have used a MATLAB toolbox in which these 40 features functions are defined. I edited some functions according to me. For that, I got the best classification accuracy. And I have used the feature selection method, that is sequential feature selection, before giving to ANN or RFC. ANN and RFC are my classifiers to classify ALS and normal classes. ANN is a artificial neural network and RFC is a random forest classifier. So in the next slide, I will discuss the SFS, which is the base of my presentation, that is sequential feature selection. These are total 40 features. Okay, the sequential feature selection method, this is a basic algorithm which I have used to select only the optimal features. For this, I got the best classification accuracy. This algorithm starts with the no feature selected, means initially we have no features, and for every iteration we add the one feature. For example, in a first iteration, if we have a 5, we just get the example of only 5 features. But in practical, we have 40 features in there. So if we start with 5 features, so X2, for every feature, we got some results for every feature. So the best results we got for feature X2. So for the next iteration, we include X2 with remaining all the features. So again, after the next iteration, we got the X2, the combination of X2 and X4. So further, at the final iteration, we got some feature set for which we got the maximum results. So this is my results for 40 features. So I got around 30 features the constant accuracy. So we don't require the total 40 features. We just used the 30 features for our classification purpose. This is the basic ANN model which we used. This structure I have created. I have used total 5 fully connected layer and 1 output layer with single neuron. And the last sigmoid function, it is used to classify normal and ALS classes. It has some probability. So the highest probability define the ALS and the lowest probability define the normal class. Okay, these are the results. The first plot shows the accuracy, the training and the validation accuracy, and the right hand side plot show the training and validation loss. I got the 95% the validation accuracy and almost 100% accuracy for the training purpose. I have used 100 epochs. So some iterations, 10 iterations, the result between the 10 epochs we got. Okay, this slide results is ANN results. I have used to classify the ANN and RFC, and this results is for random forest classifier. The 80% data is used for training and 20% data is used for testing for both the classifiers. So the confusion matrix, this is showing the 20% of data, the test data. So the left top, it is showing the false positive rate, and the right below showing the true positive results. In the ROC curve, the area under the curve 0.98, it is showing that our classifier is converts better, because how much area it is covered in ROC curve, it is getting the better result. It should be greater than 90, obvious, and it is, if AUC is very nearest to 1, means our convergence ratio is very good. Okay, this is the comparison of methods and classifier of ALS detection. There are various work for different classifiers and different methods for detection of ALS. In our proposed work, I have used the reduced feature set for SFS. For both the RFC and ANN. With RFC, I have got 92.8% accuracy, and for ANN 95.3% accuracy. Almost it is greater than the papers, the references which I have used for my comparison. Okay, this is the conclusion and future work. The finding demonstrate that classification accuracy is greater or increased when the decreased feature set is used for both the ANN and RFC. In particular, the random forest classifier obtained an accuracy 92.8, whereas an ANN model obtained an accuracy of 95.3. To improve the accuracy, further research will be done to utilize the time frequency representation for SEMG signal. So here the 1D data is converted into 2D data. So we can use the pretend model and also our designed CNN model for classification of the two classes, the ALS and the normal class, if we convert the 1D data into 2D. So my future work is on this. Okay, these are the references. Thank you.
Okay, Akansha, first of all, congratulations for such a great presentation. And
thank you, sir.
My question is that how you have, again the same question, how you have done your validation?
Okay, sir.
Which technique you have used for the validation?
Okay. So the 20% of data means the total data. Okay. So the total samples means the 151 were obtained from patients diagnosed with ALS and 151 collected from healthy. So the total samples we are getting 302. So 302 multiplied by 11 seconds. Why we are multiply 11 seconds? Because these are the samples for 1 second. So we repeating these cycles. So we have a data total 3322 something. So from the 3322 samples from 1 second, every signal, actually we segmented 1 second data. So we have 20% of these samples we used for testing or validation. In case of ANN, we name is for validation because the during training our validation is also completed. But for RFC, after training, the 20% of data showing this confusion matrix. So in the confusion matrix, the 327 plus 28, this is the 20% of the total sample.
Akansha, my question is that which technique you have used for validation?
Sir, okay, sir, optimizer.
Optimizer is not for validation, beta. Anyways.
Yes, sir, cross entropy.
Cross entropy or cross
Yes,
validation? How many fold cross validation? Okay, let it be. We are not going to detail then. Next is that you are saying that you have achieved accuracy in the comparison table. There was one comparison table with them.
Yes, sir,
with
yes,
the previous works which you have done. So here you have not mentioned the number of samples on which they have done the.
Sir, the same data set.
Then
sir,
how come you are getting 95 on the same data set, because and the one person SVM and ANN.
So my structure is different, not same.
So the number of data set will not go.
The features are different, sir. The only 11 features from raw data is selected at that when ANN is different, but I have used the total 40 features. Okay. Sir, I have used the MATLAB toolbox for extracting the features, and for Python, I have structured the ANN model in RFC.
Okay, and coming on to the confusion matrix, can you just come on to it again?
Yes, sir.
Yes, you were telling something. Which one is which category?
So true positive and true negative, false positive and false negative.
So which are true positives?
True positive, true positive.
You can tell the number.
Okay, so true positive 283.
283 are true positive. Okay, and which are true negative?
True negative 25. सर एक्चुअली मैं थोड़ा सा कंफ्यूज होती हूँ उसमें. बाकी सर ये है कि जो 283 है ये करेक्टली क्लासिफाइड है क्लास 1 की तरह. थोड़ा सा मैं कंफ्यूज होती हूँ सर इसमें. ये जो 4 हमारे टर्म्स होते हैं जिससे हम एक्यूरेसी को मतलब कैलकुलेट करते हैं, और सर ये जो 327 है ये करेक्टली क्लासिफाइड है एज क्लास 0.
when you were giving presentation also, then also you got confused.
Yes, sir.
So the best way out to remember is that
Yes,
when
sir.
we say true positive, false positive, true negative, false negative, the last word, if it is positive, then you can come with the prediction. Like if it is true positive, then positive means 1. Okay.
Okay,
And
class,
true here,
sir.
last word, yes.
Okay.
So
Last
positive
word is for
means
class.
for the prediction, what you have done. Like if you are saying
For the
true
prediction.
positive,
Okay.
so positive here is
True.
the prediction. And
Okay.
true means whether it was positive or it was not positive. So true means it was positive. That means 1 1. So here 283 is true positive.
True positive. No?
Understood? The
Yes.
last word is representing your classification, your result,
Yes.
and the first word is representing what it actually belongs to.
Okay, sir. Okay. So 283 is a true positive.
Okay.
Okay, sir.
Fine. That's it from my side. Thank you, Akansha.
Okay, sir. Thank you, sir.
Now I would like to call upon paper presenter ID 514 to present their paper. Also remain constrained to the time.
Stop share.
Is paper ID 514?
Yes, ma'am.
Say your ID proof.
Ma'am, my screen is visible.
Yes, your screen is visible to us. Say your ID proof if you have any.
Yes, ma'am. I ID proof is ma'am.
Okay, fine. You can start your presentation.
Good after, good afternoon, everyone. My name is
Turn on
Pushpan
your
Kumar.
camera, Pushpender. Please turn on your camera also.
Okay, ma'am. Okay, ma'am. I am Pushpan Kumar Bas from MTech Research Scholar from MNNIT Allahabad, and I am honored to represent my research paper titled "Utilization of Digital Forensic for Image Forgery Detection and Detection at the 12th International Carpet Signal Processing and Integrated Network." This work is a collaborated effort with my co-authors Anuja Dixit ma'am and Rahul Dixit sir. Sir. Then I will give to the next slide, and these are my outlines today. First, introduction, then objective and related work, then data set description, proposed methodology, then results and computational complexity and efficiency, then system requirement and conclusion and future works. Image forgery is the process of manipulating a image, and the goal is to mislead the owners and representatives. And common types of image forgery is like splicing, image forgery, copy move, retouching, deep fake manipulation. Here in figure 1, first and second image is original image. Then you can see spliced image. One image, first image is first image is appended into the second image. That is C is a spliced image, and objective enhancing the multi-stage deep learning framework by integrating improved feature extraction and classification techniques for high accuracy and splicing image forgery detection. Multi-stage deep learning means first I am extracting a features from ResNet 15, then extracted feature is taking input in SVM, then it's provide the output. And related work, traditional methods for image forgery detection, pixel-based method, analyze the spectrum information of each pixel to detect the anomalies. Manipulating techniques including the pixel value distribution, block inconsistencies, and color histogram to identify the difference between original and tempered image. And geometric based focus on a special properties like object alignment and geometric consistencies. And third one is a format based method, analyze artifacts from lossy compression to detect the inconsistencies, tempered image, showing compression mismatch, making these methods effective for forgery detections. And second one is a deep learning approach forgery detection. CNN based future learning. CNN are widely used for forgery detection with a pre-trained model ResNet 15 or VGG 16, extracting the hierarchical features to detect anomalies in manipulated image. Transfer learning enables these models to leverage large data set for improving the accuracy and generalize with minimal fine tunes. And second was is a combination of CNN and handcrafted features like DCT and local binary patterns. And the third is a ensemble learning approach. Ensemble learning combines multiple models such as CNN, support vector machines, or decision tree to enhancing the forgery detection accuracy and minimize the misclassifications. This approach is effectively for handling the diverse forgery types requiring different detection strategies. And data set description. In our research paper, I am using a Cassia V2 dataset, benchmark dataset, widely used for data image forgery detection, especially dataset compositions. Is the content 12,614 color image, in which 7,491 is a real image and 5,123 is a fake image. And forgery in image set, two types of image in available. First one is a splicing image and also have a copy move images. Resolution or format. Image resolution in a given image range between 240 to 160 pixels to 900 to 600 pixels, and I am reshaping all images into 224 into 224. And after because both range are both images are different number, then I am converting into same number of image for better accuracy. Then using a balanced dataset and random underfitting techniques are used in here for balancing the both real and fake image numbers. This is my proposed models. First, I am taking a dataset Cassia V2 dataset, and in data preparation, first taking categorize or taking original and fake image, then cleaning some images like some images randomly removing for maintaining same numbers. Then total images 5123 into 5123, first combine it into and then divide the data set into three parts. Training set, I am taking a training set in 18% of data. Then validation set, I am taking a validation set in 10% data, and testing set also taking a 10% data. In validation, I am using a K folder cross validation for validating the images. And future extractions, in training set, especially and contextually, here futures, many types of futures are extracting like age, colors, pattern, and so on. And fine-tune pre-trained weight for ImageNet to improve the detections. And model training optimized using the binary cross entropy and ADAM optimizer techniques. But in after extracting the future, I am using a support vector machine for extracting the futures. And evaluation matrix, after classification, evaluator matrix perform the measured using accuracy, precision, recall, and F1 scores. Access the master ability to generalize to unseen the data set. And final output, I am given an input, then it's predict its image is authentic or original or fake. Then in a result section, training was conducted on workstation features NVIDIA RTX A4000 GPU with CUDA 11.2 and CUDNN 8.1 for accelerating the optimizer performance. Here, first parameter is pre-trained trained ImageNet and fine-tune layers. I am using a ResNet 15, then last 30 layers are unfreezed. And input image size is 224 and 224 and epoch is 45 and byte size is 32. Our learning rate is 1 multiplied by 10 to the power minus 5 and optimizer techniques are used here ADAM and last function is categorical cross entropy. And I am in our model, I am taking a two data set, Kaisia V1 data set and Kaisia T2 data set. In Kaisia 1 data set, accuracy is 75 for validation result and testing is 74.5%. And Kaisia V2 data set, validation accuracy is 92.05% and testing results is 19%. And computational complexity and efficiency optimizer model size. I am using a ResNet 15 model because it's 25.6 million parameters. It is significantly lighter than the VGG 16 models and faster training time. The model trains in 45 epoch batch size, which is much faster than the DCU net because it's the third epoch batch size in 16 and better resources utilization. SBM classifier is computationally lighter than the ANR based classifier, reducing processing load while improving the efficiency and faster interface time. And system requirement Python programming language, deep learning library like Keras and TensorFlow 2.10 and hardware configuration NVIDIA RTX A4000 and RAM is 60 GB. Operating system is Windows 11 and GPU accelerators CUDA 11.2 and CUDNN 8.8. Conclusion, the proposed hybrid model, ResNet 15 and SVM effectively detect the splicing forgery with high accuracy and achieve 90% accuracy and 96.71 precision and 19.76% F1 score on Kaisia dataset. And future work extend the model to localize the forgery regions using the semantics techniques and exploring advanced machine learning techniques such as a graph neural network for forgery detections. And these are my references.
Okay, Pushpendra ji. So this was a classification problem, prediction problem. Which problem? Which problem it was?
Classification, sir.
Classification problem. Okay, and any specific reason you didn't use logistic regression, the basic algorithm? You can unshare you can unshare your screen first, yeah. Or you can come on to the PPT. The second question is that you are saying that you got a precision around 96%. Can you just come on to that number? The last slide, I guess it was. Yes. The precision you got 96%. So, do you know the difference between precision and accuracy? How come they have such a huge gap?
Sorry, sir, I am.
And under which condition you use F1? Any specific reason you have calculated F1 or by default?
No, sir. That's just I am taking a standard library. Then it's by default calculating 2 into precision plus precision into
My question is why we calculate F1? Okay, anyways, Pushpendra, thank you. That's it.
So that was the final paper presenter. I would like to thank each paper presenter who presented their paper on their hard work. It was really a fruitful experience. Also, I would now request Dr. Richa Sharma to present a sapling as a token of gratitude. I would now request Dr. Richa Sharma to present Dr. Sumit Bharadwaj a certificate as token of appreciation for being the session chair. Thank you so much, sir. Your presence really lifted the entire session experience. Also, paper presenter, your certificates will be sent to you via email shortly. Thank you for your valuable contribution. I would now like to ask for the permission from Dr. Sumit Bharadwaj to close the session.
Yes, it does.
And also, sir, we are really want to express the heartfelt gratitude and thank you for your participation in SPIN 2025. Your words and work are both inspiring for the university students and all among us. Thank you, sir.
Thank you, Radhika. Thank you, Richa,
Okay,
ma'am.
thank you, sir, for sparing your valuable time. Thank you so much.
It's always great, ma'am, to come back to my university and to come back to my organization. And looking forward to meet you all in person. Thank you. Bye, ma'am. Bye.
Always. Okay, bye, sir. Bye.
Hello, Richa ma'am. Richa ma'am. Hello.
delegates, and paper presenter present here. It is a great privilege to have Dr. Anupama Bhan with us today. I would like to invite Dr. Richa Sharma to present a sapling to Dr. Anupama Bhan. Dr. Anupama Bhan is an accomplished academician with over a decade of experience in electrical and electronic engineering. Welcome once again, ma'am. Ma'am, would you like to call upon the paper presenter, or would you prefer if I do it?
Yes, you can start the presentation.
Thank you, ma'am. Now, I would like to call the paper presenter ID 517 to present their paper. Thank you, and also keep in the mind the time constraint. Present your presentation within the time span of 10 minutes. Thank you.
Hello.
Yes, paper ID 517. Yes, you are audible. Can you share your ID proof in front of camera?
Okay, thanks. I have to. Actually, I have set background as blur. I have to check it. Can I present the paper? Because I don't know how to change it.
Okay, you can share your PPT.
Okay, thank you. This is my paper posture estimation of agriculture workers using deep learning based computer vision.
Your PPT is not visible to us. Please share your PPT. Yes, now it is visible. You can start now. Yes, it is visible. You can start.
So my paper is post estimation of agriculture workers using deep learning based computer vision technique. So in paper we have used three YOLO variants, the YOLO V8 to 11 and YOLO VNAS to calculate the key points of the human body, and based on that we have calculated RULA and RABA score, which is used as a measure of as how much stress a worker would feel when they would do certain activity. So this is the index. So agriculture constantly stands as a top three professions prone to injuries and hazards. So main goal of this paper is to design tools, the agricultural tools, in a way that the stress which is felt while using them could be reduced. The instrument could be more inclusive in nature, that a person of different heights and body forms should be able to use comfortably those tools. So this is it. So based on so it is targeted in reducing the health stresses. So we can classify injuries in two main categories: the tangible injuries and the intangible injuries. The tangible injuries, it can occur due to mishandling of farm tools, while intangible injuries, it could occur due to continuous use of work postures. Like you can see that while farmers work, they have to bend down and squat. So due to which they had their back pain and the knee pain. So we should design tools in a way that these pain could be reduced. So this is the problem statement. The improper handling of agricultural tools poses significant health hazard to workers, emphasizing the need of a systematic assessment of associated risk to ensure safer workplace practices and reduce occupation injuries. So this is the base paper which I choose, in which they use open source open pose model for the key point detection, which is one of the key stage in calculating the RULA and the RABA score. So these are the objectives: to develop a robust deep learning model for ergonomic assessment of agriculture workers, to evaluate the performance and effectiveness of the developed models. So there can be different approaches for the calculation of the RULA and RABA score, which act as a quantitative measure of qualifying the stress that a worker would feel when they would handle certain certain tools, agriculture tools. So they could be a self-report which we could ask from the farmers himself that what issue they were, or we could observe from a range and then on that conclude. And another thing is direct measurement. All these approaches have their disadvantages, and to overcome these, we have proposed a deep learning based model to calculate the key points and subsequently the rule and labor score to measure the stress felt by the farmers using their agricultural tools. So then I would go to the literature survey. So the first paper is the ergonomic posture assessment using open pores, which is one of the paper. But all of these papers that we have considered, they basically lacked a good data set that we created in this, and also they were based on the very basic models. In this paper, we have used the latest YOLO V11 and V8 model for the key point detection. So we collected different 500 plus images of agriculture workers performing different tasks, and we tried to ensure that it covers a wide variety of postures in terms of the standing, squatting, and other different forms of active postures which the agriculture workers generally maintain while they do their work. So to calculate the key points, we can use one of the models. They could be a skeleton model, contour model, or a volume-based model. In this paper, we have used a skeleton model, and we have tried to identify 17 key points: like the hip, left knee, and all of these models you can see in this pic. And based on that, we have tried to calculate the angle between those. So the main score that we calculate to measure stress is the ruler and Rayban, and it requires us to calculate the angles between different joints of the body, like the angle formed at the knee or at the elbow, and based on that we calculate the stress. So this is a methodology. First is the agriculture posted data set, then we collected it, and then we tried to apply pre-processing and augmentation techniques. It can be applied to the scaling, rotation, horizontal and vertical view. And then we tested three models, V8, V11, and VNS. And on the basis of that, we calculated the 17 key points. And on based of that, we calculated the ruler and so this is the architecture. It has the three main components: the backbone image, then there is a neck, which is responsible for picture extraction and improving a small object detection. Next is a head, which is responsible for making the final predictions. So YOLO V11 is an improved version of this that we had used, and it has given better results than YOLO V11. Next is the YOLO NES. What it does is that it uses a NES algorithm which optimizes its architecture based on the constraints imposed by the dataset. It is usually faster compared to YOLO V8 and other architectures, but based on our data set, we found out that it doesn't give that much better results compared to YOLO V8 and 11. Its architecture, its main component remains same as that of YOLO V8, but what it uses additional NAS to optimize its architecture. So this is one of the results that we got on the key point extraction. Here you can see the key points extracted, and also the degree of how well it is identifying a person. So these are the training results that we obtained for various during the training, and as you can see, the loss converges, the validation loss and the training loss converges as we are increasing the number of epochs, and this indicates that our model converges after 30 epochs, which is and also the AP and the AR also uh, reaches above 0.9 after 30 epochs, which is an indication that our model performs good. Next is a YOLO V8, the training results of YOLO V8, which also gives comparable results as in compared to V8 to V11. YOLO NES, it doesn't give that much good result as compared to YOLO, but it is faster in terms of calculation the key points. And in certain application, it may be better to use YOLO as it requires which are time constrained and require better results or better time bound results. So these are the main key points that we have used: the AP, average precision, average recall, and the map or the mean average precision at the area of intersection of 50. And as we can see that these all are good results. For YOLO V11 or V8, they are all greater than 0.9, which is a good model. For YOLO NAS, the result is not that much good. Maybe it's due to the data set maybe is less compared to the its requirement, but for YOLO V8 and V11 we got some good results. These are the references that I have used. Thank you. Hello, am I audible?
Yes, you are audible.
Okay. Any have any question?
Yes, Bahan ma'am.
Yes, ma'am, we can go ahead with the second presentation.
Okay, thank you so much. Thank you so much. You can unshare your screen.
Thank you.
Next paper ID is 547.
Do I need to share my ID card now?
Yes, you can share. If you have, then you can share.
So I will share it because I have blurred the background first. I will change it, and then I will show up. Share.
Hello.
Hello.
Yeah, we have paper ID 547.
Okay. Say your ID proof if you have.
Yeah. Is it visible?
Yes, it is. Okay, fine. You can
Yeah.
start.
Yeah. Good afternoon, everyone. I'm Palaniappan, a final year undergraduate student at BITS Pilani, here to present our work on high precision trigonometric algorithms for the Fawcett number system. The Fawcett format is a novel number system proposed to be a possible substitute to the traditional IEEE 754 standard. Given its novelty, there is a lack of dedicated algorithms to compute trigonometric functions for Fawcett. In our work, we propose to use the Cordic method for the efficient and accurate computation of trigonometric functions. After reviewing multiple Cordic architectures, we propose a modified Cordic scheme specifically tailored for Fawcett. Cordic, or coordinate rotation digital computer, is a shift and add algorithm that efficiently computes trigonometric functions. The core idea here is simple. When a unit vector is rotated by an angle theta, the x and y coordinates of the resulting vector correspond to cos theta and sin theta respectively. Now, instead of directly computing these values, the Cordic method decomposes theta into a sequence of smaller elementary angles. Then, by applying a series of micro rotations, the algorithm gradually converges to the desired angle. These elementary angles are pre-computed and stored in a lookup table, reducing computation overhead during execution. After relevant transformations, these steps can be mathematically written as shown on the screen. So when x and y components of the vectors are updated as shown on screen, they converge to the corresponding cosine and sine values of the angle they have been rotated by. The Fawcett number system provides a more flexible alternative to floating point arithmetic by dynamically adjusting bit allocations for different numerical ranges. A Fawcett representation consists of 4 fields: the sign bit, the regime, the exponent, and the fraction. The regime here is the defining part about Fawcett, which encodes the scale of the number using a sequence of identical bits, which adjusts the dynamic range. This dynamic structure of Fawcett's enables them to represent numbers more efficiently than IEEE 754 floating point numbers, particularly in domains requiring high precision. Compared to floating point numbers, Fawcett have several advantages. They allocate bits more flexibly, providing higher precision in critical ranges. They eliminate special cases like NaN, infinities, and subnormals, ensuring that every bit pattern represents a valid number. And in computations involving small differences, POSIT suffer from fewer rounding errors, making them ideal for iterative algorithms like CORDIC. A 32-bit POSIT can have equal or greater precision than a 32-bit float in certain numerical ranges, making it well suited for high precision computations. One of the biggest challenges with using POSITs in CORDIC is catastrophic cancellation. When two nearly equal POSITs are subtracted, small errors can grow exponentially. Since POSITs adjust this precision dynamically, they may not always provide enough bits for very small numbers, leading to inaccurate results over multiple iterations. The POSIT format also adds computational complexity. Unlike floating point numbers, where bit allocation for exponent and fractions are fixed, POSITs change dynamically. While this allows for better precision in some cases, it makes implementing iterative methods like CORDIC more challenging. To develop a modified CORDIC scheme for POSITs, we have conducted a thorough analysis of popular CORDIC schemes, such as the angle recoding method, the radix4 method, and an existing CORDIC algorithm designed for POSITs, called the fast forward iteration with Squares method. A proposed algorithm enhances the rotation mode codec by leveraging an optimized angle recoding scheme based on a greedy approach. In the original method, angle recoding requires exhaustively scanning the entire lookup table in each iteration to find the angle closest to the residual. While effective, this approach is computationally expensive and slows down execution. To address this, our algorithm introduced a conditional check that compares consecutive angles in a sorted LUT. Instead of scanning the entire table, we perform a linear traversal, selecting the largest angle closest to the current residual. This significantly reduces LUT access, lowers computational overhead, and improves processing speed. However, a key challenge still remains: cancellation errors in small values. As iterations progress, the angles become increasingly small, leading to catastrophic cancellation, where values reduce to zero and introduce irreversible errors in trigonometric computations. To mitigate this, we adopt the POSIT quire format as recommended by J.P. Lim and his group in their work. The 512-bit quire accumulator is designed for the POSIT Pareto system. Using quires to store the residual dramatically reduces cancellation errors, ensuring higher precision and stability in computation. As I mentioned previously, a modified approach is inspired from the angle recoding technique. For a given angle, a proposed scheme reduces the iteration count while also outperforming the original method. The proposed method approaches R to 0 in 13 iterations, whereas angle recoding needs 18. This enhanced accuracy can be attributed to the reduced number of rounding and cancellation errors achieved by reducing the number of operations and the use of quire-based calculations. The proposed CORDIC algorithm is evaluated based on accuracy, computational efficiency, and numerical stability. A proposed CORDIC algorithm is evaluated based on accuracy, computational efficiency, and numerical stability. We measure the accuracy by utilizing the multiple algorithms to compute trigonometric values for every representable POSIT. We then compute the average error for sine and cosine functions. Additionally, we compute the ULP distance for each input with its corresponding exact value, computed using the MPFR library. We then measure speed and computational efficiency through metrics like LUT access, iteration count, and overall latency. The proposed algorithm delivers remarkable accuracy for sine and cosine computations. It achieves the lowest average error for cosine, improving by 44% over the basic approach, and significantly reduces the error for sine, cutting it down by 62%. While EAS performs slightly better for sine due to its extensive angle set, our method balances accuracy across both functions. It also records the lowest max error for sine and ranks among the top for cosine. When looking at exact POSIT counts, the proposed algorithm provides the highest overall, meaning it delivers perfect accuracy for a large portion of inputs, making it the best choice for cosine and a strong competitor for sine calculations. This indicates that the proposed algorithm can deliver perfect accuracy in 51% of the total input space for sine and 45% of the total input space for cosine computations. Beyond accuracy, our algorithm is also much more efficient. It reduces iterations by 76% compared to the basic approach, while keeping LUT calls low at just over 5 per iteration, compared to 50 in angle recoding and a massive 315 in EAS. Radix4 offers a balance between iterations and LUT calls but sacrifices accuracy. While maintaining slightly lesser average iteration count as annual recoding, the proposed method reduces average LUT calls from 50 to 5.27. Our method achieves EAS near accuracy while being far more efficient, making it the best option for fast and precise cardiac computation. In conclusion, we propose a fast and efficient cardiac method for posits that can be used in signal processing, radar systems, and other real-time applications like digital filters. Thank you. I'll be taking questions if there are any.
Yes, any questions from the audience?
Nice presentation. We can go for next one.
Thank you.
Now I would like to call paper presenter 562 to present their paper.
Hello.
Yes, Mr. Sumesh, you can say your ID proof. Okay,
Yeah.
thank you. It is visible to us. Okay, thank you.
Okay, thank you.
Okay. Paper ID 562, please turn on your camera.
Good afternoon to ma'am. May I be
Good
visible?
afternoon. Say, yes, you are visible. And say your ID proof also. Okay, fine. You can start.
Thank you, ma'am. Good afternoon to all. My paper ID 562. The title is Removal of EOG Artifacts Using Empirical Wavelet Transform and LC Filter. Coming to abstract, the portable electroencephalogram systems used in healthcare for brain signal analysis due to their affordability and ease of use. However, they often face challenges with EOG artifacts from eye blinks which can affect the diagnosis accuracies. To address this, we propose a hybrid framework combining empirical wave, fixed frequency empirical wavelet transform and LC filter. This method removes the EOG artifact while preserving the and without losing the low frequency EEG information. And the performance metrics, we have evaluated the correlation coefficient, that is 0.96, and the MEI mean absolute error 0.27, and the signal to artifact ratio SAR is 1.12. The proposed method tested on synthetic and real EEG data sets. Coming to introduction, the main motivation for to this EEG helps understand the brain disorders and motor imaginary functions, cognitive load, and other EEG applications to recording the brain activity to control the physiological systems. In any BCI applications, to remove the EOG artifact is a vital task before analyzing the EEG signals. The main biological artifacts are electroocculogram, electrocardiogram, electromyogram. Apart from this, electroocculogram is very near to the eye blinks are very near to the skull, so it is very continuously interface with the EEG signals with low frequency spectrum. So since the eye blinks occur instinctively every 5 seconds, so removing these artifacts is enhance the EEG signal quality. Some additional traditional decomposition methods and traditional filter techniques were used in previously, like adapt noise canceller and median filter. Some other techniques were the circular and singular spectrum analysis and discrete wavelet transforms. So the main proposed method is we have collected data from BCI computation 428 data set, that is a real data set, and another one is the synthetic data that is collected, that one collected from the Mendeley data set. Then we have applied the fixed frequency empirical wavelet transform. So we fixed the different frequencies that are mentioned in that function. The first band is 0 to 4 Hz, and next is 4 to 8 Hz, next 8 to 12 Hz, next 12 to 20, and 20 to 60. Total 5 frequencies we have given. So based on that, we decompose the contaminated EEG signal into 5 intrinsic mode functions. So then we have extract the kurtosis feature that is very useful to identify the whether the artifact is there in IMF or not. So based on the kurtosis feature, we identify that this is a non-artifact signal, this is the artifact signal. Once that finalize the artifact signal, again apply to SG filter. So SG filter, the function is the smooth test by the that artifact signal, and final output is the filtered EEG signal. So this is first one. The figure represents the EEG signal, that is a contaminated signal. That contaminated signal applied to fixed frequency empirical wavelet transform that gives the 5 intrinsic mode functions, that is the empirical wavelet transform 1, 2, 3, 4, 5. These 5 are the decomposition of the contaminated EEG signal of figure 1, this figure 1. Then we have applied the existing filtered techniques with our proposed method. So first one is our data and with median filter and EMD DW filter and ASSA filter coming to the SG filter. So figure 3 shows the simulated results of all conventional methods with proposed method. So compared to other methods, our proposed methods effectively remove the UOG artifact from EEG signals. So below figure that is represents the power spectrum density plots of conventional methods with the proposed method. So based on proposed method, we have evaluated different performance metrics, correlation coefficient and mean absolute error, evaluated from the simulated results of real data and filtering methods of a recovered signal using all methods. The proposed methods achieve the correlation coefficient of 0.89 for synthetic data and 0.96 for the real data. So similarly, the mean absolute error also 0.13. Different SNR values, so minus 4 dB, 0 dB, and 4 dB respectively. The significant improvements are seen over the conveniential algorithms. So these are the results, different filters methods and SAR values. So median filter, AMD DWT filter and ASSA filter and proposed DWT SC filter achieved the 1.12. That is better than compared to existing methods. So conclusion and distinction. The proposed method EWT and scavenging goal filter method effectively identifies and remove the UOG artifacts from contaminated EEG signals. So in brain science, the EOG remove is very, very important to analyze the EEG signals for any diagnosis. So the results show that hybrid approach superiority with performance metrics, including CC, MAA, and with different SANLs. These findings confirm that EWT SG method is a reliable, efficient solution to remove the EOG artifact from EEG signals. So these are the references I have used. Thank you.
Yes, any questions from the audience? I think no more questions. Okay, thank you so much.
Thank you.
That was the final paper presenter. I would like to thank each paper presenter who presented their paper on their hard work. It was really a fruitful experience.
I would now request Dr. Richa Sharma to present Dr. Anupama Bhan a certificate as a token of our appreciation. I would request you to remove the share screen.
Please wait for a while.
Okay, thank you so much,
Thank
ma'am,
you,
for
ma'am.
sparing your valuable time. Thank you so much.
Thank you, ma'am.
Paper presenters, your certificates will be sent shortly via mail.
We wanted to express our heartfelt thank you for your participation in SPIN 2025. Ma'am, your presence and words were inspiring, and thank you so much, ma'am, for being here.
Thank you.
Thank you.
Okay. IT support, you can stop the recording now.
Ma'am.
Yes.
Richa ma'am.
Yes.
You want me to end the meeting now?
Yes. Yes. Please.
Okay. Is there any session? Any other session to go,
No.
ma'am?
No. No. No.
All right.
You can end the
Then I'm
meeting.
close. Okay, ma'am. Okay. Thank you, ma'am.
Okay. Thank you.